Okay, this is, well, an afternoon-long BGP tutorial. It's going to be in two sections. First section is probably more covering introduction. It expects some knowledge of BGP, in other words, that you've heard of what it's all about already. And it takes you through how BGP is used within a service provider network. The second half of the tutorial after the break is covering more about how ISPs deploy BGP within their network, and it also looks at some of the issues that are being, I suppose, are faced by ISPs these days. So it's very much introductory leading on to intermediate tutorial. If you're a BGP guru, think about giving this tutorial the next time, because I've been doing this for a few NANOGs now, and well, it'd be nice to see some other people standing up here rather than just me doing it. Second thing is I must apologize. I have got an extremely bad cold at the moment. My voice still works, which is quite amazing, but my ears are all a little bit funny, so if I have to take a pause every now and then to well, catch my breath or recover and so forth, that's what it's about. It's one of these things. I did a big trip around the world before this one, and well, I didn't catch anything at all. I get back home to Australia. My friends are delighted to see me and promptly give me the cold. So here I am with whatever is on the run in Australia at the moment. Right, okay, let's move on. Presentation slides, I don't know if they're up on the NANOG website yet, but they should be there. Yes, they are, which is great. They're also up on the URL that I put on the screen, which I can't quite point to, but it's there. Feel free to download those. In fact, the FTP site I've put up there has got a load of other presentations as well, which are all perfectly entitled to take, use as you wish. There's more than just this BGP tutorial. There's a whole load of other things as well, which hopefully you'll find interesting. The other thing is, because this tutorial is being recorded, if you want to ask questions, please do so, but please use the microphone that's been parked in the middle of the room there. Also, if you just, as is convention here at NANOG, if you state your name and affiliation, then at least we know, or at least the audience watching will know who you are and so forth. Okay, so those are the four topics we're going to look at. Probably going to have a look at the first, at least the first two bullets before the break, and looking at the rest after the break. So what is this BGP thing? Well, BGP is really the routing protocol that's used to exchange routing information between different networks that make up the internet today, and indeed different networks that may not have anything to do with the internet. But it's the routing protocol that's used to allow different operators to exchange the prefixes they have with each other. It's an exterior gateway protocol as opposed to an interior gateway protocol. Exterior gateway protocol is used between different networks. Interior, of course, is used inside networks. The BGP RFC was updated recently. RFC 4271 describes pretty much the standard as it is today. That replaces RFC 1771, which was, well, written years and years and years ago, and which virtually nothing complied with anymore. But 4271 is pretty much the state of the art. There's also an implementation report described in 4276. 4277 describes some operational experiences in using BGP4. Another thing I want to introduce at this stage is the autonomous system. Autonomous system is what I call BGP's fundamental operating unit. BGP works between autonomous systems. It doesn't really understand or care about routers and people and so forth. It sees the autonomous system as the entity, and that exchanging information between autonomous systems is how it actually functions. In fact, AS is used to uniquely identify networks that have a common routing policy. So the next slide pretty much describes this collection of networks with the same routing policy. They're using a single routing protocol. There's usually single ownership, trust, as well as administrative control. Usually Not always. You see some cases where there's more than one organization using a single autonomous system. But by and large, you'll find that one AS will map onto an organization. And of course, it's identified by a unique number. Now, the AS number is a 16-bit integer. The first 64,000 or so are assigned by the regional internet registries. And the last 1,000 or so are private autonomous systems. So a bit like private and public address space. You have your public address space, which is used on the public internet. You have your private address space, which is only intended for networks not connected to the internet. Likewise with AS numbers, you have your public AS numbers, which are used within the internet, and you have your private AS numbers, which can be used for networks that are not connected, or at least not advertised to the internet. First and last one are reserved. 32-bit AS numbers are coming soon. This is more a frequently asked question in these sort of tutorials that I do. Ooh, we're just about to run out of 16-bit AS numbers, getting up as far as about 41,000 now that have been assigned to the registries for further distribution. The current state is the 12th revision of the AS 4-byte draft. I don't know what the current situation is. I mean, I noticed the draft expires last May, as in last month, but it doesn't seem to be in the RFC editor queue, so maybe there's another revision due coming. But anyway, that's coming real soon now. The two BGP implementations I know of that support 32-bit AS numbers. So expect this coming to a router, probably within the next year or so. So as I was saying, AS numbers are distributed by the regional internet registries. You can also get them from your upstream ISP, who's a member of one of the registries. I think for most of you, this will be ARIN. As I was saying before, up to 41,983 have been handed out to the registries at the moment, so you'll start seeing some of those higher numbers appearing in the routing table over the next few months. So that leaves about 22,000, 23,000 AS numbers before we actually run out. Various people have made estimations as to when we will run out. That's probably going to be the next 3, 4, 5 years, just depending how quickly AS numbers are used up. But I would say within the next 5 years we would have exhausted the 16-bit pool, and the 32-bit pool will start being used. Interestingly enough, of the 42,000 AS numbers that have been distributed to the regional internet registries, only about 22,500 are visible. So yes, there'll be a few thousand that are in use, but not publicly visible. And then there'll be another, I suppose, there'll be another few thousand have not been handed out by the registries yet. And then there'll be another several thousand that are, not used at all. They've been assigned to a service provider or an organization, but are simply not announced to the internet. Okay. Moving on from AS numbers, we now know what the AS numbers are for, basically describe the network that we have. How does BGP actually do some, function? First thing is, it runs over TCP. It uses TCP port 179. This probably falls into the filtering 101. Many of the newer ISPs that I help set up the networks struggle with getting BGP set up for the first time, because they've got the pretty serious filters running on their border router, and BGP doesn't come up. And of course they forget that they need to allow TCP 179 through the filters in both directions. So that's probably the first thing to be aware of. BGP is a path vector protocol. Not really going to spend any time describing what that is. Just suffice to say that BGP pays attention to the AS path, the actual path of autonomous systems going through the network, and it uses a lot of that path information for policy. BGP relies on incremental updates. If there's a change in state in the network, BGP will pass on that particular change. it doesn't distribute the entire BGP table as it sees it. In fact, the entire BGP table is only distributed when a BGP process will start up. Otherwise, you have incremental updates. You've also got this internal and external BGP concept. And a lot of the workshops and tutorials I do teaching ISPs how to use BGP, I try and encourage people to think of them as actually two separate routing protocols. Because they actually function quite different ways. Internally in the network, you have one particular use for BGP. Outside your network, talking to other networks, you have a slightly different implementation of BGP. It ends up looking a different thing, and it tends to be easier to think of them as two separate things. Where the two autonomous systems talk to each other, where they peer with each other, for example, between router A and router C, that particular link is generally called the demarcation zone, or DMZ, DMZ, whatever. It's a demarcation zone. It's the bit of the network that's jointly owned, or nobody owns, or in the case between B, D, and E on the diagram there, it could be something like a local exchange point, where three different autonomous systems come and connect to each other over a shared medium. That's generally the demarcation zone. How BGP works, it learns multiple paths via internal and external speakers, picks the best path, and installs that in the forwarding table. So how it picks the best path and so forth, I'm going to cover later on. The BGP has a set of rules that it follows. Best path is sent to external BGP neighbors. You want to tell your other BGP neighbors, your external neighbors, what you think the best path to a particular destination is. In fact, all the destinations you know. And actually, when you want to implement policies in BGP, influencing this best path selection process is how you go about applying the policy. And that's really how any of the policies are applied in BGP at all. You have this set of rules for picking the best path, and by manipulating the rules or changing the rules, you can apply your policies. We'll see that a bit later on. Now, the differences between external and internal BGP, as I was saying a few minutes ago, I like to encourage people to think of them as slightly different routing protocols, because they are used completely differently in internal networks and between networks. IBGP is used to carry some or all of the internet prefixes across your own backbone. And it's also where you carry your customer prefixes as a service provider. Okay, I say ISP here, but it can be any service provider. External BGP is used to exchange prefixes with other autonomous systems. And that's where you implement your routing policy. It's very rare for any service provider to have any routing policy running within their network. So you don't really see any policy applied to IBGP. The model is something like this, I suppose. You have your internal network, you use something like OSPF or ISIS so that the routers in your internal network can find each other, so they can see each other, so they talk to each other, so that they can send traffic to each other. That's all fine. But then you also have IBGP to let your internal routers and all your customers connected to these internal routers actually reach the internet. How do you get this internet information, well, your own information out to the internet and internet information back to you? Well, you use external BGP for that. So I separate them out like this. So you see the eBGP jumping between the different buckets. That is what eBGP does. It transfers prefixes from one autonomous system to another autonomous system, whereas IBGP will provide you with the reachability across your particular network. Your IGP, whether it's OSPF or ISIS, simply allows your routers to talk to each other. That's actually a pretty important bit, which I'll come back to in the second half of the presentation. Too many ISPs still in many parts of the world seem to think that IGP is where you can put the whole internet routing table because, well, why not? It works, I can configure it. But in fact, 190,000 prefixes in OSPF doesn't work wonderfully well. So I'll talk about that again in the second half. Now, external BGP is basically BGP speakers in different ASs talking to each other, so as per the diagram. So router A talking to router C, this is an external BGP session here. By default, these two speakers should be directly connected. So again, in this example, you see there's, well, basically a single wire or Ethernet that is joining router A and router C in AS100 and AS101. You never run an IGP between eBGP peers. Again, some of the common mistakes are people say, "Ooh, I can run OSPF on the demarcation between AS100 and AS101, and that will give me reachability." Of course, they run OSPF in their own network, and of course AS101 is running OSPF in their network, and what you end up with the IGPs from each network polluting the other one, just for a little bit of convenience of running an interior protocol on an external point-to-point link. So as I always say, IGP means interior gateway protocol, interior means inside. Inside means not outside. But people still seem to be quite happy running some type of interior routing protocol outside the networks. So, as I say, never run an IGP between eBGP peers. Internal BGP, here the BGP peer is within the same autonomous system. So your BGP neighbors are all in the same AS. And in this case, they do not need to be directly connected. And there's an important reason for that. You've already got OSPF or ISIS allowing all the routers to connect to each other, all the routers to talk to each other. Each router in the network knows how to get to the other one because that reachability information is in OSPF or ISIS. So BGP doesn't care about the detail of your network infrastructure. All it cares about is, oh, well, you've got 10 routers in your network, and this is the information that I'm getting from those. The IGP takes care of how it actually gets there. So again, by default, the iBGP speakers need to be fully meshed. This is fine for small networks when you're starting off with BGP. Once you start running the 1,000 or 2,000 router networks, this fully meshed becomes a bit of an issue. Again, we'll talk about this a little bit later on. But by default, from the start, iBGP speakers need to be fully meshed. This was one of the rules. The reason being was that iBGP speakers only originated connected networks. So if you have customers connecting to this particular router, their address space you would originate into iBGP, and it would be announced to all other iBGP speakers. Another thing was they would only take prefixes from external BGP speakers and pass them on to internal neighbors. One of the things that was not allowed at the start was an iBGP speaker taking a prefix from another iBGP speaker and passing it onwards. The idea being to try and avoid having routing loops way back in the early days. But as we'll see later on, this doesn't scale too well. So it looks something like this in the picture. iBGP doesn't care what your topology looks like, but the important thing is every iBGP speaker needs to speak with every other iBGP speaker. If you don't, you end up with basically what are called black holes in the network. You've got missing bits of connectivity. Customers of yours cannot see other customers of yours. In fact, it's, again, harking back to troubleshooting tutorial in BGP. One of the common issues, one of the common iBGP problems that people experience is customers not being able to speak to other customers. It almost always points to some kind of iBGP problem, and it's usually because an ISP has forgotten to include a newly added router into the full iBGP mesh. That's usually what the problem is. It's certainly the first question I ask when somebody asks me for help. And I usually don't get any answer after that, so it usually kind of suggests that this has been the issue. Anyway, the second thing with setting up iBGP is the requirement really, or I suppose the common sense requirement to peer with loopback addresses. When you set up iBGP, you can set up iBGP to run between the physical interface on the router. But what happens if the physical interface goes down? For example, this is going to be hard to show, but say this link goes down and you're running iBGP between those two routers. Well, if the physical link goes down, the IBGP would drop down because the router would see the remote interfaces or the remote neighbor as having disappeared. If you run the IBGP between a loopback interface, for example, if you run it between the loopbacks, so from this loopback to that loopback there, well, when the physical link between these two routers goes down, the original router just says, well, you know, this is the loopback, how do I get to it now? And OSPF comes along and says, well, you can go the other way. Okay, you can just go from here round to there and then back round there. Okay, so the result is the IBGP session stays up. The next hop is still reachable. The remote loopback is still reachable. The IBGP session carries on going. So this gives you a very stable design. Here in North America, it's probably not so much an issue with having unstable infrastructure, but I visit many parts of the world where the infrastructure is really difficult for people to actually keep going. Having a good OSPF design ensures that a lot of these people can keep the IBGP running nice and stably. Okay? You want to have the IBGP as stable as possible. If it's not stable, then your customers have reachability issues within your own network. So setting up peering between the loopback addresses is actually really, really important. If your router or your implementation doesn't have a concept of a loopback address, try and pick an interface that's not going to be dependent on your topology like this, for example. So in the Cisco speak, the loopback interface is generally the easiest for us to use. Okay, next thing I want to look at for BGP are the BGP attributes. And this is, basically I've subtitled it as information about BGP. With every prefix that gets announced between different autonomous systems, you have a whole list of other information that can get sent with the prefix as well. First one I want to look at is called the AS path. Each autonomous system that the prefix is passed through is stored in the AS path attribute. So the AS path attribute is just part of the prefix, a part of the bundle that includes the prefix. Every AS that the prefix passes through will append its AS number into this AS path attribute. So for example, if a prefix starts in AS100, say 180.10/16, gets passed on to AS200, then 300, then 500. If you look at on the router in AS500, you see that 180.10/16 has got those three numbers after it. So 300, 200, 100. That is the AS path. So the number on the right is the origin AS. The number on the left, the 300, is the AS that you've actually heard the prefix from. Okay? So that will list the autonomous systems that the prefix has traversed. And the one on the right, most importantly, is the origin AS. That's how you find out who originated a prefix onto the internet. The origin AS is the one that does that. Okay? Why we had the AS path? It's there for loop detection. That was the important reason. You don't want to end up with a situation where, because the way the internet is designed, the internet is not really a tree structure. It's autonomous systems have a very, very complex interconnection with each other. And of course, you're going to find a situation where you connect an autonomous system that probably will see your AS through different paths. You don't particularly want your AS, or routes from your AS to be announced back to you from an upstream or a peer or something. So the idea was to try and stop having this sort of loops appearing within BGP. And the third reason, of course, for the AS path is to apply policy. We'll see that a little bit later on as well. There's a lot that you can do to apply policy, both matching and rejecting, to do with the AS path. Just a bit more detail on the loop detection. AS500 connecting back to 100, for example. Well, 180.10/16 was originated by AS100. Now, if you're sitting on a router in AS500, you connect back to AS100, and, well, what do? Well, AS500 could probably announce 180.10/16 back to 100. 100 will see the incoming announcement, and it would say, well, hang about, 180.10/16, I originated that. That's my prefix. So if there wasn't any loop detection at all, the router, or AS100's routers, would simply take the announcement coming from AS500 and maybe propagate it further on, if there's, in the absence of any other decision making. It may even propagate it further on. What actually happens is the border router there that connects to 500 will drop the prefix because it sees the origin AS being the same as the local autonomous system. In fact, you get some implementations that would see that they're peering with a particular AS, say a router in AS500. They spot that they're peering with AS100, and so they won't actually send any prefixes originated by AS100 back towards AS100. So they kind of preempt the loop detection that AS100 is going to carry out anyway. Again, just for efficiency of announcements across the link. Now, the next hop is the next attribute that I want to look at. The next hop is quite literally that. It's the IP address of the next router along the chain. Now, the next hop is really an attribute that's shared between autonomous systems. What you'll find, for example, in this case, router A announces a prefix towards router B, say 150.10/16. Router B will see the next hop, or will say that the next hop is the IP address of router A on this point-to-point link. Okay, that's the next hop address. One thing you've got to note for internal BGP, and it's again another common mistake that implementers of BGP in service provider networks will make, is that they forget that this next hop address is transported across IBGP as well. You don't get the next hop address changing at router B when the prefix is passed on to router C. That's a pretty important one to remember. So if you look on both router B and router C, you see the next hop address for 150.10/16 is still the IP address of router A in that diagram. Okay, you've got to watch that one. Yes, there are ways of changing the next hop address, but the default action is to retain the next hop address like this. For IBGP, kind of got to watch how the IBGP next hop functions. We've set up a full IBGP mesh in this particular case. Router B is announcing, well, originating 120.1.1.0/24. We've set up IBGP between the loopbacks. So the prefix that B is announcing will have the next hop address of the loopback interface of router B. So if you go on to A or D, for example, you'll see the next hop is the actual loopback. The next hop is not the WAN interface or the Ethernet interface of router B. It's the actual loopback because we're running the IBGP between the loopbacks. So this is actually a pretty useful feature because it lets you disconnect your IBGP from what your infrastructure looks like. As I was saying earlier, if any infrastructure links break, your interior routing protocol will reroute around that break. The loopbacks are always going to be reachable as long as the router is reachable. So this ensures that all your internal connectivity remains stable, all your customer networks remain reachable, and so forth. Third-party next hop is one to be aware of. For example, if we're running, say, eBGP between router A and router C, and there's an eBGP going between A and B, well, if B is announcing the 120.68.1/24 prefix on towards A will simply re-announce that prefix on towards C in the absence of any other filtering and so forth, but it will retain the next hop because the IP address of router B, 150.113, is on the same network as 150.112 and 150.111. The idea being here that it's more efficient. You don't need any extra configuration and so forth. The only thing is, if you didn't actually intend, say your AS200, you didn't intend to peer with AS201, you might end up with prefixes that you didn't particularly want to receive. So third-party next hop was It's probably a neat labor-saving device. I've used it myself many times over the years, but it can also lead to a little bit of problems as well, especially at internet exchange points. So just to make you aware of what that particular is. If the LAN or the shared media has the same IP address, router A in this configuration will not change the next hop address to its IP address on the LAN. It will leave the address that it actually learned the prefix from. Okay, so a summary about the next hop attribute. The IGP needs to carry the route to the next hops. Watch out for that in IBGP. We're using recursive route lookup. So again, remember in the IBGP example, the idea being we really want to unlink BGP from the actual physical topology. And of course, it lets the IGP make the intelligent following decision. IGP is going to reroute in a matter of seconds, again, depending on the timers you've chosen in your network. BGP is a slowly changing thing. It's not going to make instant changes if something breaks in the network. Okay, it's deliberately designed to make changes slowly so that you have some kind of stability. You don't particularly want slow changes to happen within your own network. You want a broken backbone link to be routed around as fast as possible, certainly within a matter of seconds. So unlinking IBGP from your physical topology makes a large amount of sense. Okay, next attribute is the origin. I've put historical in inverted commas. I mean, it is basically a historical attribute. It's not used anymore. At least, we don't have any official use for it. What it was for was to allow from the transition from the old routing protocol that predated BGP. This was called EGP. The origin attribute had 3 values, or it has 3 values, still has 3 values. These are IGP, EGP, and incomplete. The origin IGP means that the BGP prefix has been generated within BGP itself. So in Cisco speak, it's appeared from the BGP network statement. Whereas EGP means it actually has come from EGP itself. Incomplete means, well, it doesn't mean it's incomplete, it means it's come from another routing protocol altogether. So you may have redistributed from, say, a static route or a connected route, or even, if you're really brave, from OSPF or ISIS. Again, newcomers to BGP find these names completely confusing because they see IGP and think, oh, okay, OSPF, but what's that got to do with it, and so forth. Especially when we're told, well, IGP is interior gateway protocol and EGP is exterior gateway protocol. And what does an incomplete origin mean, and so forth. So that's what I always say to people, don't worry about it too much, because these days, quite frankly, there's not really any use for it. Some ISPs still use it. Some ISPs still find it funny to set origin E just for entertainment value, but I don't know. Anyway, moving swiftly on, aggregator conveys the IP address of the router or the BGP speaker which generated the aggregate route. But the only use for it really is for debugging. It lets you find out which router created the aggregate, but apart from that, it has no real use whatsoever. It's certainly not used in the BGP path selection process. So it's simply there. If you want to find out who generated a particular aggregate, it will tell you who did that, which router did that. So the next one, this one is really important. This tutorial is part of a series of 3 tutorials. This is basically the introductory, the techniques one. The second one I do in the series is all about multi-homing. And local preference is probably one of the most important attributes when it comes to multi-homing, when you have got more than one connection to another network. Suppose you've got this situation on the screen. Okay, you're sitting on AS400, you're sitting on router C, you want to get to AS100, who's announcing 160.10/16, and well, that's what you're faced with. Which way do you go? It's a bit like driving along the freeway and you come to a junction and the signs both point, one to the left, the other one to the right, and they've got the same destination. Which one do you choose? Well, as a human being, you can probably make a mental choice. And that's, you know, we're given brains to do this sort of thing. Routers aren't. They're pretty dumb devices. They do what they're told, like computers. So you give a choice to the router, it needs a decision. It needs to know. It can't just say, oh, well, let's go for this morning, let's go this way. And for this afternoon, let's go that way. They don't have that capability, at least not yet. So we've got this situation. What do we do? Well, this is where the local preference comes in. You, the operator of AS400, can actually determine which way you want the traffic to go from router C or from AS400 to get to AS100. And you use local preference to do that. If you mark the incoming announcement of 160.10/16 coming in from AS300 and from AS200 with a local preference, you can then tell your network which way to go out. So in this example, I've said, well, the announcement coming in from router E, I'm going to set local preference 800. The announcement coming in from router D, I'm going to set local preference 500. And so if we sit on router C, we see two entries for 160.10/16. One of them for 500, the other one for 800. For local preference, the highest local preference wins. So the 800 value beats the 500 value. So router C has a best path at last. So it can be told, yes, we're going to send all the traffic from C to AS100 through the B to E link and AS300. So that's what local preference does. It lets you control how you send traffic out of your network. And basically in the BGP path selection process, it's the number one. Okay? Okay? You have ultimate control over how traffic goes out of your network. Nobody else can override it. If somebody else is doing stuff with BGP policy that you don't like, you simply slap a local preference on top of it and that will override it. Okay? So it's the most powerful, most important attribute. Just a summary of it, it's a non-transitive attribute. It's only really used in your autonomous system. If you announce a prefix with a local preference to your neighbor, he'll overwrite it with his own default value. Okay? It's used to influence BGP path selection, determines the best path for outbound traffic. So you apply local preference to inbound announcements. Okay, that's an important one to remember. When I stand up here and I say it, and I've done BGP more years than I care to remember, it's simple enough. But I remember the first 6 months when I was trying to get to grips with all this. Now, which way was it? Was it inbound, outbound, and which way was traffic, and so forth? It's just a case of having to try and memorize how these work. Also, the highest local preference wins. Cisco iOS default is 100. Other implementations may use other defaults. So you need to be aware, especially in a multi-vendor environment, what the different defaults are, and even try and set them all the same so you don't get confused. The next attribute is MED, or multi-exit discriminator, or those of us who've been around too long, we still call it metric. Multi-exit discriminator, well, it lets you discriminate between multiple exits. Take this example. You're in AS201, you've got an address block you're announcing to AS200. You want to tell AS200 how the traffic is going to come into AS201. Okay? Well, of course, AS200 could set local preference to pick one of the paths. But if they don't do that, you can actually influence how the traffic comes into your network by using MED. Okay, so again, without any configuration being set here, router C has got a decision to make. Routers don't like decisions. They have to know absolutely what they're going to do. So what the operator of AS201 does, he sets MED of 1000 on router B, he sets an MED of 2000 on router A on the outbound announcement of 120.68.1/24. Router C will see two paths with different MEDs, different metrics. And, well, in this case, just to confuse, the lowest MED wins. So the best path inbound will be from router C to router B. So lowest MED highest local preference. So why is it lowest MED wins? Well, if you look back into OSPF or IS-IS, there the lowest metric wins, because certainly for OSPF, the lowest metric interface means the highest bandwidth, generally. Okay, so I suppose the analogy is to be there so that you've got some chance of trying to remember it. Unfortunately, for some people, it's like, okay, which way around? Is it highest metric or lowest, or highest local preference, lowest, and so on. So it really is a case, early implementers, early adopters, trying to implement BGP for the first time in the network really need to be aware of that it's the highest local preference that wins, it's the lowest MED that wins. Okay, summary of all that, it's a non-transitive attribute, but it works between autonomous systems. Okay? If you learn an MED from your neighboring ISP and then pass that prefix on to another ISP, another autonomous system, well, they're not going to hear that MED that you learned. It's also, which was a bit of a problem, it's an optional attribute. See, local preference was, because it was only applying inside your network, it was set for any prefix that you learned, so it wasn't an issue. But if you announced a prefix to your neighbor, you didn't have to set an MED. And that, well, made it a little bit interesting, as we'll see in the next slide. Used to convey the relative preference of entry points to the network determines the best path for inbound traffic. It's only compared if paths are from the same AS. But, well, you know, in the usual case, you have some people saying, oh, well, but we want to use it to compare paths from different ASs for the same prefix. So, well, Cisco then added the knob BGP always compare MED, and that allowed comparisons of MEDs from different ASs, because some people needed that functionality. Path with lowest MED wins. Absence of the MED attribute implies an MED value of 0, according to the RFC. But, well, that was recently. RFC 1771 never actually said anything about what the MED value should be in absence of the MED being set. So that meant that every vendor did their own interpretation. So what happened was, well, Cisco said, well, you know, okay, if no MED is sent, we're going to assume the MED is 0. Other people said, well, you know, if there's no MED sent, then, well, the ISP probably didn't think the MED was important at all, so we'll make it 2 to the power 32 minus 1. And then other people made it 2 to the power 32 minus 2. And then as soon as you have all these different implementations pairing with each other, you end up with an MED mess. And there have been various discussions over the years about the metric confusion and the different peering problems that people have had because of making assumptions about MED values and so forth. To the extent that you really find these days that MED is not used much at all. You really don't find that many people use it because it makes assumptions about what your peer is up to. So, as I say, potential for metric confusion. In all my travels, I find that very few people are using metrics anymore these days. And the replacement really has been community. Again, I tend to find that more people are using communities to indicate policy decisions that they would have previously indicated using MEDs. So what's a community? Well, it's described in RFC 1997, so it's been around quite a long time, probably since about that year at least, 1996, 97. It's a transitive attribute, and it's also an optional attribute. It's a 32-bit integer, generally represented in real life, though, by two 16-bit integers. Human beings aren't very good at handling 32-bit integers, whereas two 16-bit integers separated by a colon is probably a more human-friendly form. So you tend to find the format used in the internet these days is your local AS number, or maybe your peer's AS number, colon, and then some number that you choose yourself or your peer has specified. Of course, there's some reserved communities, so anything beginning with 0 and ending with 65535 is a reserved community. What they're used for? They're used to group destinations. So if you've got a group of customers or maybe a group of peers that you want to apply some uniform type of policy to, or maybe peer with or not peer with and so forth, then you can put them all into the same community. So I've got loads of community examples coming up much later on in the presentation, just to give you some idea of how ISPs actually use them when they deploy BGP. But generally, it's used to group destinations. See, in the old days before communities, what we would do is we would get different AS numbers for different bits. We would probably have a transit service in our network. We'll probably have an aggregation service in our network. We'll probably have a dial-up service in our network, and each one went into a different AS, so we could apply different policies between the different autonomous systems and what we wanted to do with each class of customers. When communities came along, this became many orders of magnitude easier to configure. You didn't have to juggle multiple autonomous systems within what was effectively one network. So, as I said in the last point there, it's actually very useful in applying policies within and between autonomous systems. It's an extraordinarily useful tool, probably one of the most useful tools that have come along for BGP, certainly in my time using it. Because I remember what it was like beforehand, and it was pretty difficult. And then all these tools started appearing in the mid to late 90s, which made life so much easier, at least from the policy side. Anyway, how do they work? How do you implement them? Well, here's a sort of example. Say you're an ISP, AS300, you've got a couple of customers connecting to you in router C, AS100, AS200. They're announcing two prefixes to you. They land on router C. Fine, you set up your filters and so forth. Now, if you wanted to announce these prefixes towards, say, AS400, AS400 is connecting to you at router E. So what would you do? Well, normally you would set up a filter on router E that says allow 160.10/16 and 170.10/16 through to AS400. Then you set up a peering relationship with ISP2, but you're not going to give him access to your customers for whatever reason. So then you've got to set up a filter when he comes along with 200.10/16, put that filter on router E to deny his address block, and so on and so forth. What happens then when AS100 comes along and wants to add another prefix announcement towards you? Well, you update your filter on router C, you update your filter on router E, you update your filters on router D. You end up updating your filters all around your network all the time. And having run an ISP before communities were invented, we had to do this sort of thing all the time. It quite literally meant updating BGP filters, which meant, well, in those days, it meant doing a hard reset of the BGP session, which in those days meant doing it during a maintenance slot, which meant that, well, if a customer wanted to add prefix on, which day was it? Let me see, say Thursday at 9 a.m., and your next maintenance was Tuesday at 4 a.m., he got to wait the whole weekend, which, well, I suppose back in the early 90s it didn't really matter so much because internet was still a toy. But these days, I think if you told somebody that, they would go up the wall and across the ceiling and call you all sorts of things as well. So it was pretty hard to manage. With communities, it becomes much simpler. Because what happens? Well, your customers, you stick into community 300:1. 300:1 is our customer community. So the prefixes that come in from AS100 and AS200, we just tag them with community 300:1. The filter on router D pointing towards ISP2, just deny community 300:1. The filter on router E going towards AS400, just permit community 300:1. We don't need to put any specific prefixes in anymore. So when AS100 comes along with its extra prefix, well, the only change goes on router C. We add his new prefix into our community, and everything else just happens automatically without changing any router configurations, without changing any BGP settings, without having to reset any BGP sessions or anything like that. So there's this fairly significant labor-saving device. So that's an example of how communities might be used. There are also several well-known communities out there. In fact, there are four. The first one is no export. If you tag a prefix with a no export community, it means that that prefix will not be advertised to any eBGP peers. Okay, so if you've got some prefixes that you don't want to announce to eBGP speakers, simply tag them with no export community, and your eBGP neighbor will basically strip those prefixes out. So it's quite a handy way of, well, not quite automatically, but certainly doing some filtering. The no advertise community is basically don't advertise to any BGP peer whatsoever. So maybe you have a prefix coming in from a neighbor that you don't want to advertise to any BGP peer. Well, yes, one way you can do it is put filters on all the BGP peers. The other way you can do it is just simply slap a no advertise community onto that particular prefix. The router will automatically drop that prefix. No export sub-confed basically means don't export outside a sub-autonomous system in a confederation. We'll have a look at confederations a little bit later on when we come to the scaling BGP bit, but that's only used there. And the final one is a more recent one, is the no peer community. It's not implemented anywhere at all that I'm aware of, which is a great shame, but well, it was a nice attempt to try and reduce the size of an internet routing table for multi-homing purposes. So you can read all about that in RFC 3765. 2 slides on, I'll show you how the no peer community works. This slide shows you how the no export community actually works. For example, if you're multi-homing to your upstream, as several people do, you're probably multi-homing by 2, 3, 4, 5 or more different connections. The way that you would do your load balancing in this particular example is you would subdivide your address space into pieces as well as announcing your aggregate. And that would ensure that traffic will go down each of the links. Okay, but obviously because a more specific prefix will attract the traffic over the aggregate. So you could announce maybe a third of your address space on the link from A to D, a third of your address space on the link from B to E, and a third of your address space on the link from C to F, as well as announcing your aggregate. Now normally if you do that, well, you announce the aggregate as well as the 3 sub-prefixes, and your upstream just announces the whole lot to the internet. But the 3 sub-prefixes provide no extra information to the internet at all. Okay, you've got your address block. Announcing the detail inside that address block provides no useful information. So why bother announce it? Okay? If you put the no export community, well, attach the no export community to those sub-prefixes, then router G and your upstream will automatically strip out those sub-prefixes. They see the no export community attached to the prefix and they will drop it automatically. So that lets you do multi-homing between your upstream, leaking all the address space that you need to leak to achieve the load balancing that you want to achieve, but without polluting the whole internet routing table in doing so. Okay, so that's the main use for no export community. I've seen some people use no export community for giving preference for filtering, whether they want to announce prefixes to particular peers of their upstreams and so forth, but I see that one as very fraught with danger, as it has ended up certainly with lots of black holes and in routing and so forth. The other one is the no peer community, which I think is really neat, but then I thought was a good idea, but no vendor has implemented it that I'm aware of, and vendors these days seem to only implement things if customers really, really ask for them and wave lots and lots of dollars at them, and nobody's done it. So if you're interested in this, go and wave lots of dollars at your vendor. But the no peer community, the whole idea behind this was you could announce sub-prefixes to your upstream. If you're multi-homing to, say, different upstreams, I've got B, C, and D as upstreams here. You're announcing all these different sub-prefixes again for traffic engineering purposes, but you don't want the, say, the default free zone or the core of the internet to see all these sub-prefixes. Okay, for example, E doesn't need to see all these sub-prefixes because it could be so-called tier 1 ISP or something. Whereas B, C, and D probably do need to see what these sub-prefixes are. So you'd announce your sub-prefixes with no peer. Router B has only got one neighbor, that's an upstream, whereas router C and router D peer with each other. So the peering they would mark as a peer connection, whereas a C to E link would be just a normal upstream connection. So between C and D, prefixes tagged with the community, no peer will get dropped, whereas on C to E, the prefixes will, sorry, I got that slightly wrong. The C and E also peer with each other. The C to E, again, are marked as no peer, so the prefixes will get dropped, whereas B has got no peers, if you like, so all the prefixes will get sent through to E. The idea being is, again, to keep the local traffic engineering, the local subdivision of address space out of the Internet core. But as I say, nobody's implemented that and nobody's really asked for it, so it was a nice attempt to try and save the size of the Internet routing table, but that's basically where it's ended. Anyway, so implementation details of the community attribute. It's an optional attribute. This is where, again, you've got to be careful. There are several BGP implementations out there, and they're all different. Some implementations will send communities to IBGP peers by default. Some don't. I mean, sending communities with an IBGP makes endless sense, I think, but again, some implementations don't, and it catches a lot of people out. If you're talking to your upstream ISP, you're sending a community, and he doesn't support them. Well, all your communities get dropped, even your no export ones. So you may send a prefix with no export to your upstream, assuming that he's going to drop it, and they don't. It gets leaked out into the Internet. One of the things I do in my spare time is do the weekly routing report that appears in the NANOG mailing list. And sometimes when we see the different leakages or an ISP emails me and says, oh, I'm not leaking all these prefixes, it turns out it's somebody not honoring a no export community. Some implementations send communities to eBGP peers by default. Some don't. So again, you've got to watch that. But say being careless can lead to community confusion. So you need a consistent community policy within their own networks, especially multi-vendor ones. And don't just assume that your peers are going to support communities because they are there. Okay? There are a lot of ISPs that simply don't support them. Some ISPs even claim to have never heard of communities, or they think it's something else altogether. Like maybe NANOG is a community. Well, okay, but it's not a BGP one. So, need to inform people if you're going to use communities within your network. Now, the BGP path selection algorithm. These are basically the steps that BGP goes through to try and figure out what the best path is. I've put in the one here basically from Cisco iOS. Well, yeah, I was going to say the RFC 4271 has a particular definition of what the path selection protocol is. Each vendor has added their own little bits and pieces to it as well, but the same core principles remain there. I'm not saying that Cisco's gone and completely changed it from what the standard is. It is compliant with the standard, but it has extra bits to deal with some extra bits in iOS. The first one is probably pretty obvious. Do not consider path if there's no route to the next hop. I mean, if you can't get to the next hop, why on earth are we going to use this as a valid path? That's what that says. Okay? That catches out people who haven't implemented IBGP properly. Remember I was saying that the next hop in IBGP is, well, let's learn from outside the network, or a prefix learned outside the network is transported through IBGP. But if you don't actually have that external address reachable, then, well, the path's not going to be used. So people go, oh, well, but my path's in there, but why is BGP not using it? And that's usually the reason. The second one is weird to Cisco. Do not consider IBGP path if not synchronized. iOS by default used to have this synchronization thing. Thankfully, the most recent versions don't have that anymore, so it's generally not a problem. For ISP networks, BGP, or internal BGP, is never synchronized with OSPF. It never, ever needs that, so it's not an issue for us. But again, if people are using older versions of the software, forget to switch off this synchronization nonsense. They run into this particular one, and BGP doesn't do anything at all. And they can't figure out why, because the configuration is all right. The third one, the highest weight. Weight isn't really a BGP attribute, which is why I didn't cover it. But it's a little bit like local preference, but only works on the router. So it's not really an attribute because it's not passed from router to router. But it lets you distinguish between different paths to a prefix, but locally on the router. So obviously, if you've got a weight appearing here, the highest weight will win. So it's a bit like local preference. I call it local preference, or the router's local preference. The first real one, as I mentioned before, highest local preference. So the highest local preference will win. So if you have two paths or more paths to the same destination, the one with the highest local preference will win. If the local preference is the same, we then move on to the next step. We prefer the locally originated route. So if we originate it locally versus being originated somewhere else altogether, we prefer the locally originated one. Seems kind of sensible. The next one never actually appeared in RFC 1771, but it is in the more recent one, is shortest AS path. Why jump through 30 autonomous systems to get to a destination when you can go through 2? Okay, I've exaggerated, but that's the point. You want to pick the shortest AS path to get to a particular destination. The AS path length is the same. We then move on to the next one. We pick the lowest origin code. Well, origin code, as I was saying earlier, these days shouldn't really matter anymore. Some ISPs still use it for intense little detail within their own network, but we're no longer in any transition between EGP and BGP, so it shouldn't be an issue. So we can generally safely ignore this one. If the origin code is the same, then we move on to the next one, and that is at lowest MED. MED is, by default, only compared if the paths are from the same AS. Okay, if the paths are from the different AS, we would normally jump on to the next step. But if you have configured this always compare MED knob that was asked for years and years ago, then you compare it no matter what the path is. Okay, some ISPs have found that particularly useful. Also, if the BGP deterministic MED has been set up, again, that's a recommended good practice, as we'll see right at the end of the presentation. The paths are ordered before comparing. I'll explain what the deterministic MED is much later on. Again, that's a recommended good practice thing to do. So we order the paths before comparing. As I say, otherwise, the MED is only compared if the paths are from the same AS. So if MEDs are the same, we move on. We prefer the external path over the internal path. So if we're sitting in a router that's got eBGP, external BGP to reach the path, as well as an internal path, we're going to prefer the external one. Clearly, the destination is outside our network, so we're going to dump the traffic off our network. That's basically what this says. Next one, path with the lowest IGP metric to the next hop. That says pick the highest bandwidth. Okay, lowest IGP metric is generally the highest bandwidth. So we're going to pick the highest bandwidth to the next hop. So it might be highest bandwidth within our own network, or highest bandwidth within our own network to get out of our network. Okay, if the IGP metrics are all the same, then we look at the lowest router ID. Okay. If the router IDs are the same, well, we're starting to get desperate. We're starting to get really desperate. It's then the lowest neighbor IP address. Now, the theory is that IPv4 addresses on a network are unique, so the lowest neighbor IP address should actually give us a unique answer. This is what I was saying before. Routers aren't really built in with any kind of logic, intelligence in them. They need a if-then-else decision tree. Okay, and this is the entire if-then-else decision tree for BGP. I jumped over the shortest cluster list. One of the scalability, BGP scaling features is a route reflector, which I'm going to cover a little bit later on. So when you have a route reflector set up within your network, then it introduces one more step into the path selection process. So in multi-vendor environments, it gets a little bit more interesting. You need to make sure that the path selection processes are understood for each brand of equipment, because each vendor seems to like doing things slightly different. So be aware that you don't end up with a routing loop between two of your favorite vendors simply because the path selection process is slightly different. So use whatever knobs you have to try and make them behave the same way. Oh, and watch out for MED confusion. That's probably pretty important. Try and make sure that the MED, if you're going to use MED, make sure that the defaults are the same, or even don't rely on defaults. Just come up with your own scheme of what these MED values should be between you and your neighbors. Okay, so applying policy within BGP. So this is giving you all the control that you hopefully will require within your network and dealing with other autonomous systems. So policies are applied to influence the BGP path selection process. So you can manipulate BGP attributes really to manipulate the path selection process. That's by and large what most people are doing. A policy is also about determining which prefixes are announced or blocked. There may be certain parts of the internet you don't want to get access to. Seems to be network 41 is the favorite at the moment. I've just come back from AFNOG and the ISPs there using network 41, having terrible trouble getting access to some parts of the internet. So whether that's deliberate or on purpose or accidental, I don't know. But that's part of BGP policies being implemented but not being kept up to date. Determine which AS paths are preferred, permitted, or denied. There's particular autonomous systems or ranges of autonomous systems that people probably don't want to get access to, or you don't want to prefer through particular paths. So again, that's about applying policies. And you can also determine route groupings and their particular effects. So decisions you generally find are made on prefix, AS path, and community. Those are usually what people are manipulating to get what they need. So most implementations of BGP will have tools to apply the policies. So they've got prefix manipulation, prefix filtering, AS path manipulation, AS path filtering, also community attribute setting and matching and so forth. And also implementations will have different policy language so they can do various matching and setting various conditions based on those matches and so forth. Again, all these are dependent on what your vendor gives you and even dependent on software release. So I'm not going to go through them in fantastic detail. The configurations examples that I put in are there more to try and exhibit a point rather than trying to show how to do it on any one particular implementation. I'm sure if you go knocking on the doors of your favorite vendors, they'll tell you how to do all this. Before I sort of dive a bit more into some of the detail, I want to just touch a little bit on BGP capabilities, as we'll need that in the BGP scaling part. One of the ways of extending, BGP is usually, is by using this BGP capability function. This was added in, well, it was RFC 2842 describes it. I need to look up when that was actually, but it's been relatively recent. BGP was really started off for handling IPv4, unicast IPv4, and that was pretty much it. Then the multicast folks came along and was like, oh, we want to do BGP, or use BGP to handle around multicast prefixes. Then the IPv6 folks came along and was like, oh yeah, we can use BGP for handling IPv6 prefix round and about. And then the MPLS folks came along, and so on and so on. So all these extra things have been added to BGP. So part of this addition, rather than getting each implementation do a major rewrite just to add a new feature, there was this capability functionality added where when a BGP speaker opens a new session, it can ask its neighbor, hey, what capabilities do you support over and above the default in BGP? So when a BGP session is opened, it can say, well, a speaker will say, look, I support this and this. What do you support? And so on it goes. Each BGP capability has a different number attached to it. So the first 64 are assigned by the IANA by IETF consensus. The next 64 are first come, first served. And the final 128 are vendor specific. So the final 128 are basically vendor comes up with some cool new feature which hasn't gone anywhere near the IETF yet. And so they go and implement it there, and so on. So the current ones that I know of, and I checked these a few days ago, capability code 1, well that means multi-protocol BGP, so more than just unicast v4. So if your BGP is capable of doing multicast as well, then, well, you've supported the multi-protocol. You support the multi-protocol capability. The second one is quite interesting. That's one of the BGP scalability bits I'm going to talk about in a little while, is the route refresh capability. So that's got capability code 2. Cooperative route filtering capability, that's still internet draft. I have no idea where that's going. I should look up and see where it is actually at. RFC 3107, don't know anything about the next one. I don't know who's implemented it. Then we've got the graceful restart capability. That's still sitting as internet draft. Support for 4 octet or 32-bit ASNs. That's still sitting internet draft, but I imagine it's going to become RFC sometime soon. 66 is gone. 67 support for dynamic capability. I need to read the draft to remind myself what that was about. But those are the current state of the different capabilities that can be supported. So the multi-protocol extensions, well, that's a whole different world. I'm not going to talk about any of these whatsoever. This is just really BGP tutorial. There's the V4 multicast, there's the IPv6 one, there's the V6 multicast, of course, not to mention VPNs. As I say there, it can be another tutorial, it can be another many tutorials. Route refresh, I'm going to cover shortly. Others are still in development, as far as I'm aware. So now let's move on to scaling BGP. I highlighted some problems at the start about BGP scalability, and the first one really, which is a major issue, well, I was there and got, well, not completely burnt by it, as I wasn't really involved, but I suffered from it, was scaling the iBGP mesh beyond a few peers. These days, well, we've got all these nice scalability techniques, but back in, again, the early internet days, I don't mean this to sound like an internet history thing, but I realize each time I give this presentation that I've been around probably for a long time. And a lot of my tales are back in the old days when we didn't have any of this stuff. We didn't have any of the iBGP scaling techniques. The only way we could do iBGP was full mesh. And, well, the full mesh famously broke once upon a time, and, well, some people had to work really hard over a very short space of time to come up with an alternative solution to allow the iBGP mesh growing. And the network at that stage was not really that big at all. How do you go about implementing new policy without causing flaps and route churning? Well, again, I hinted at that at the start when I was talking about communities. We had to do a hard reset of the BGP session. If you do that today, you're going to knock your network out for, what, 5 minutes or so? Again, depending on your hardware. But if you do a hard reset in BGP, you may as well reboot the router. So that's a major issue. You can't do that in today's network. And generally, how to keep the network stable, scalable, as well as simple. So I'm going to look at these three: route refresh, route reflectors, and confederations. So the route refresh. Well, every time you do a policy change in BGP, you need to have some way of telling your neighbor that this change has happened. Because remember, BGP only sends updates. So if you've changed your inbound filter to block a whole range of prefixes, but your neighbor has already announced those prefixes towards you, how are you going to get, well, your network and everybody else to know that this change has happened? If you just change your inbound filter, you've still got the prefix on your internal BGP. Well, the only way really to get rid of the prefix is to get a BGP update message from your neighbor that says, well, this prefix has gone. Well, he's not going to do that because he's still announcing the prefix. So what you have is you have an inbound filter that somehow got to get rid of this prefix from inside your network. So what you would do in the old days was you would shut down the BGP peering. You would then bring up the BGP peering, and your inbound filter would block this prefix that you were hearing from your neighbor. Okay? As I was saying, a hard reset is probably not such a wonderful idea. It consumes CPU, 190,000 prefixes in the BGP table today. It would take a few minutes to load that up, obviously depending on your router CPU, but it takes significant time. Severely disrupts connectivity for all networks. Well, yes, I mean, it'll basically cut you off the network for the time that the BGP session needs to come back. So hard reset's not really a wonderful idea. So what you want is a soft BGP reset or a route refresh, where the BGP peering remains active, but it only impacts the prefixes which are affected by the policy change. So the way the route refresh works, basically when you need to do a route refresh, you send a message to your neighbor that says, please send your BGP table again, your entire BGP table. So rather than asking your neighbor, well, rather than your neighbor sending incremental updates, he sends you his entire BGP table. Okay, and that's what the route refresh capability is all about. It's automatically negotiated at the time you set up the BGP session. All implementations can now do this, thankfully. So you don't need to configure anything. Okay? So when you bring up a BGP session, the capability is right there. Doesn't need any extra memory, doesn't use any extra resources on the router. It just happens. So RFC 2918 describes the route refresh capability. General recommendation is to try and use this capability if it's supported. But I don't think it's any issue these days of saying if it's supported. Virtually everything I know does support it. And it's definitely good for the internet. It's good for your own network as well, because it doesn't cut your customers off the net for a significant amount of time. If you find that your peer or your neighbor is still running an ancient implementation that doesn't support it, then you'll find that most vendors will have, well, an implementation workaround that will let you handle this. I mean, Cisco's version is this soft reconfiguration configuration command, which basically stores a copy of what your neighbor sends to you before you actually apply your inbound policy. So that can be pretty useful as well, but it consumes memory on the router. Okay. Again, when I'm teaching BGP, especially in workshops, I find it really hard to try and convince people to actually use the route refresh capability. People are far too easy just resetting the whole BGP command. I suppose the CLI could be improved to do the, are you really sure you want to do this? It's the same when you type a reboot into the router, it actually asks you if you're sure you want to do it. Maybe a clear of the BGP session could ask the same question. So anyway, the dynamic reconfiguration, probably most of you are using automatically without even realizing it. But it's been a pretty good development for BGP. Hard reset, consider it the same as a router reboot. Next one, route reflectors. This is all about scaling the iBGP mesh. So you've got 13 routers in your network, that's 78 iBGP sessions. So that's probably fine, fair enough for a small network these days. What happens with an extremely large network? 500 routers? 1,000 routers? 1,000 routers, you're just short of 500,000 iBGP sessions. Anybody fancy maintaining 500,000 iBGP sessions on the router? I mean, the configuration gets bad enough even with 13 or 12 neighbors to maintain, as on the diagram. So having a large number of iBGP sessions to maintain gets too hard. And of course, the more sessions you have, the longer it takes to bring up the iBGP mesh as well. So as I was saying, 1,000 routers there, you've got nearly 500,000 iBGP sessions. So it doesn't scale. Two solutions. Route Reflector came second. The Confederation came first. And that was basically coded up very, very quickly, almost as an emergency to rescue one certain large ISP, which I was part of way back then. I mean, that was a pretty serious disaster for them. And it was a serious disaster for us as a customer because it meant our network went up and down for, I don't know, 4 or 5 days until they got the thing actually sorted. Confederation came first, as I was saying, so I'll cover that next. I'll cover Route Reflector first, because I think it is much simpler to deploy and it's much, much simpler to run. I won't really enter the discussion as to, well, which one should I deploy in my network today? You tend to find, as in the OSPF versus ISIS debate, that people who have experience with one technique are quite happy with using that one technique wherever they go. So you can follow the spread of confederations throughout the internet, as you can follow the spread of route reflectors throughout the internet, as you can follow the spread of ISIS versus OSPF throughout the internet. So I'm not going to get into that one, but I'll just explain really what they both do. So how does the route reflector actually work? Well, in normal BGP, normal IBGP I should say, routers A, B, and C would have a full mesh with each other. Okay, so if router A introduces a prefix into the IBGP, it would announce it to B and to C. Router B hears prefixes from the outside world by eBGP, it will announce it to A and to C. So that's normal IBGP full mesh. Now, if we make router A a route reflector, what that does, it says, hey, router A, if you learn prefixes by IBGP, you can pass them on to other IBGP speakers. So external prefix comes into router B, B sends it to A is now a route reflector, so A will pass the prefix on to router C. Okay, so that's the only change we've made. We've said A is going to be a route reflector. It seems so simple. And that's the thing, when the route reflector thing actually came out, what was it, 96, thereabouts? We were looking at it and we thought, well, why didn't they do this from the start? And it's like, I've never really known the answer to the question. I suppose nobody really thought about it and so forth, because it seems such a beautifully simple solution to the scaling problem. So that's really what it is. So router B and router A talk IBGP with each other. Router A and router C talk IBGP with each other. B and C no longer have an IBGP session. That's the big win. Now, if you think with a large network, you've changed your IBGP scaling problem from being more or less an n-squared problem to just an order of n problem. Okay, so it's not such a serious problem anymore. So looking at it in a little bit more detail, so we've got a little network there in AS100. It's got 12 routers in it. Now, normally we would have each router having 11 IBGP sessions with each other if we did the full mesh. But now we've converted it into this route reflector thing. So in the middle of our network, we've got the route reflectors right there. So A, B, and C are the route reflectors. And scattered around them, we have the clients. It's an interesting way that the network has been designed like this, because this layout should look familiar to those of you who are using OSPF. Okay? And it's familiar because you design OSPF like this. You have an area 0 for OSPF, and then you have the other areas scattered around area 0. And the route reflector design tends to map very, very nicely onto how OSPF networks are designed and implemented. And generally I find these days, if somebody's deployed OSPF across their backbone, it's very, very, very easy for them to simply go and deploy an IBGP route reflector system on top of it. If we look at some of the terminology and so forth, so we've got the reflectors in the middle. These are the routers that will take IBGP prefixes and pass them on to other IBGP speakers. There are some rules. The clients basically sit on the edge of the network and they only talk to the route reflectors. And the rules are fairly straightforward, but you need to think about them. Router A as a route reflector, it can receive paths from clients and from non-clients. It will pick the best path. If the path is from a client, it will reflect it to other clients and to non-clients. Okay, which is fine. If the path is from a non-client, it will only reflect it to clients. The important thing to remember, a route reflector will not take a path heard from a non-client and pass it on to another non-client. It only takes paths from clients or non-clients, non-clients and pass them on to clients. Okay, that's an important one. So router A is not going to take a prefix it learns from B and pass it on to C. It's assumed that the route reflectors in the core in this diagram are fully meshed. So your route reflectors in the core still need to be fully meshed. Actually, the lines I've drawn there indicate the IBGP sessions. I mean, as I say, BGP doesn't care what your network infrastructure looks like. So here I've indicated the IBGP sessions. The clients are at the top, the clients at the top here all talk to router A. The clients over there talk to router B, and these clients here are talking to router C only. Notice one thing with the router C route reflector group. I've got the clients talking IBGP with each other as well. You can do that if you wish. Certainly in the early days, this was something that we had to set up. I don't remember the reasons why now. There was some restriction in the very first implementation in iOS, but that got removed very, very quickly. So the clients were fully meshed. You still find that some ISPs, especially if they're setting up the route reflector across a wide area, they tend to still fully mesh their clients just in case connectivity to the reflector goes down, because they still want to have their regional network functioning, which is a fair point. And the route reflector whole setup is described in RFC 2796. I think that's being updated. I seem to remember something about that. Anyway, RFC 2796 describes the route reflector setup. How we do the topology. Again, this is probably more my recommendations. Every time I do this presentation, somebody comes up with something different, but anyway. Try and divide the backbone into multiple clusters. If you've already deployed OSPF, or to some extent ISRs, you can quite easily map a route reflector setup on top of that. Have at least one route reflector and a few clients per cluster. The route reflectors need to be fully meshed. Again, as an example I showed before. The clients in a cluster can be fully meshed if you want to, but it's not really necessary these days. Don't touch your IGP. There's never any need to touch your IGP. Some people try and redesign how their IGP is done, but if your IGP is properly designed from the start, the route reflector setup will sit quite nicely on top. The two new attributes that have been introduced, there's the originator ID, and that is the router ID of the originator of the route into the local autonomous system. So the route reflector will set that attribute. And there's a cluster list attribute, which is a little bit like the AS path, but it lists the route reflectors that the prefix has passed through. So if you have multiple route reflectors in your network, you'll see a list of the route reflectors that the prefix announcement has gone through. Sorry, I was choked there. It's best to set the cluster ID from the router ID. So the router ID is the address of the local router, generally set from the loopback. It's best to set the cluster ID from the router ID. Some ISPs use their own cluster ID assignment strategy, but this needs to be well documented. I could tell stories about all the problems of cluster IDs clashing and so forth. I've demonstrated this in workshops and so forth, and it's quite simple to see what can actually go wrong. It's similar to having the same AS appearing twice in the AS path. One thing I should have said at the start, I'm going to overrun 15 minutes because we started 15 minutes late, but I've already overrun my 15 minutes overrun, so I'm going to finish this bit and then we'll have the break. Multiple route reflectors can be configured in the same cluster. We don't actually advise that because multiple route reflectors in the same cluster implies that the route reflectors have the same cluster ID. Now this is all fine and good if the two route reflectors are sitting in the same point of presence. But I've had to come in and troubleshoot networks where the route reflectors, one was sitting in one city in the west, and the other one was sitting in the other city in the east. And there was a large distance between them, and by large I mean several hundred miles, if not more. Trying to troubleshoot problems there when the link between the two cities has gone down, and all the issues that this causes, you just really don't want to go here. So my advice is always to achieve redundancy in your route reflector cluster by having overlaid clusters. The next slide shows exactly what I mean by that. Overlay them, have one route reflector and a group of clients, and that group of clients can also talk to another route reflector and do the overlay like this, which is generally a lot safer. Because then even if the link between the two route reflectors disappears, you don't end up blowing part of your network to pieces. So that's the sort of thing I'm driving at. Interesting enough, I've done this pretty much from day one. from when route reflectors appeared. And when I joined Cisco and I said, well, this is what I've been doing, they went, huh? But you can't do that. Well, I don't know. I've been doing this for the last 2-3 years. And, well, there's never really been any issue with it. Then, of course, as more and more ISPs deployed, some of the larger networks, especially in Asia, we've run into huge problems with having the router IDs and the cluster IDs set the same for the 2 route reflectors in the cluster. So now I generally recommend people do your redundancy in your route reflector, but have 2 overlaid clusters in the same point of presence, pretty much as I have here. So, for example, you've got the green lines show 1 route reflector cluster, so cluster 1. The red lines show the other route reflector, so cluster 2. Okay, so route reflector benefits, solves the IBGP mesh scaling problem, doesn't touch packet forwarding because it's just about how BGP passes prefix across the backbone. Normal BGP speakers coexist. The only routers that need to know about the route reflector capability are the actual reflectors themselves. You can have multiple reflectors for redundancy. It's dead easy migration, multiple levels of route reflectors. I've not yet come across any network, any installation that has found a limit. And some of these networks have been like several hundreds of routers, quite happily. Where to place them? Again, my advice from bitter experience, mostly in troubleshooting, is always follow the physical topology. Setting your 2 route reflectors in 1 point of presence in 1 corner of the country and then expecting to serve 20 other points of presence in 20 other cities from those 2 route reflectors is stupid. But you'll be amazed how many people try and do that. I don't know why they do that, but they do that. Always follow the physical topology. Set up your 2 route reflectors in each of the cities. Fully mesh them. Routers are bigger these days. They can handle having 40 or 50 IBGP neighbors. It'll guarantee that packet forwarding won't be affected. It'll guarantee you more sleepful nights rather than sleepless nights. So a typical ISP network has point of presence has 2 core routers. Make the core routers the route reflectors. It's not a major effort for them. And then have 2 overlaid clusters. Okay. Core routers have the fully meshed IBGP. And then all the other routers in the point of presence are basically the clients in that particular cluster. How to migrate? Well, when we migrated many years ago, 10 years ago, well, we just did it in 1 maintenance slot hit. That was easy. I wouldn't recommend it, but we managed then because we were bold and foolish and young, I suppose. Try and do 1 cluster pair at a time. So set up what your route reflector is, eliminate the redundant IBGP sessions, have 1 maximum route reflector per cluster, overlay your 2 clusters, your 2 core routers, work with 1 point of presence, get happy with it. Once you're happy with it, move on to the next one. If you have a lab, start in your lab. Do that first. Now, the idea behind confederations was rather than doing anything weird with scaling the BGP mesh, like using route reflectors, what you did was you took your AS and you chopped it up into lots of pieces. So this is basically dividing the autonomous system into several sub-autonomous systems. And what you did was you talked eBGP between all these sub-autonomous systems, but as far as the world's concerned, you're still 1 autonomous system. Okay, so the way you solve the IBGP mesh problem is chop it up into lots of smaller IBGP meshes and then pure eBGP with each one. And it's not really eBGP as in what I've just been talking about. It's an eBGP, but you preserve the next hop information across the sub-AS, you preserve local preference, and you preserve MED. So some people call it eIBGP, which just further confuses things as far as I'm concerned. But you don't need to touch the IGP. You can leave your OSPF or ISIS quite happily. RFC 3065 describes the confederation spec. So you're visible to the outside world as a single autonomous system. This is generally called the confederation identifier. Each sub-AS uses a number from the private AS range. So you've got 1,023 autonomous systems that you can use. I don't know of any ISP who has split the confederation up into that many sub-ASs, but you can certainly do that if you want to. IBGP speakers in each sub-AS are fully meshed. So all you've really done is you've taken the full mesh and split it up into lots of smaller full meshes. Total number of neighbors is reduced by limiting the full mesh requirement to only peers in the sub-AS. So again, what sort of topology could you use? You could, again, make each confederation a point of presence, or say for North America, you could make it, I don't know, West Coast, East Coast, Central, Canada, whatever. Or you can also, or whatever system you want to try and come up with. But anything that subdivides the full mesh into something that's more regionally manageable. Interesting thing is, within each confederation sub-AS, you can use a route reflector. I mean, that came along later on, about 6 months afterwards it came. And you can actually use a route reflector within the confederation sub-AS. So you get the benefits of both worlds if you want to. What does it look like? It looks something like that. Your AS200, and well, we'll split AS200 into 3 sub-ASs. So you've got 65530, 65531, 65532. Configuration snippet to show you the sort of configuration example. Your router, of course, will sit within the sub-AS. The only concept it has of your real autonomous system is through the next line, the BGP confederation. BGP confederation identifier, and that lets the router know what the real AS is. And then you list other autonomous systems that are also part of the confederation, just so that you know whether you're peering with an eIBGP peer or a real eBGP peer. And then you list all your other neighbors as you normally do. Migrating from a full mesh IBGP to using a confederation is major effort. Well, certainly on Cisco's. I don't know about other implementations, because, well, your BGP, your AS number is incorporated as part of the BGP configuration. So you can't just change the AS number and have all other configuration intact. You've got to do a fairly major re-architecting. So whenever people come to me asking about, oh, well, I need to scale my iBGP mesh, I've got my 50 routers, what do I do now? It's always route reflector, because that is, well, put it simply, a no-brainer transition, whereas moving over to confederation is a lot harder. Confederations have this AS path thing as well. If you're sitting inside a confederation, you'll see this AS sequence. Yes, they have got the real AS number, so you've got the AS200 coming in there from the outside world. And as the prefix transitions through the confederation sub-AS, you see, whoops, it's very difficult doing this. You see, as well as the 200, you see the confederation sub-ASs incorporated in curly brackets, just to let you know it's a confederation sub-AS. But by the time you pop out the other end at router H over here, the outside world just sees you as AS 100. Okay, they don't see any of your internal structure, which is, pardon me, the whole idea. Okay, but within the confederation, it looks as though you're running several little networks talking eBGP to each other. The route propagation decisions, well, the same as with normal BGP. So peer in the same sub-AS only goes to external peers. From external peers, it goes to all neighbors. So it just looks like a normal eBGP, iBGP thing within a sub-AS. Okay. The comparison thing, I'm not going to get into the argument. I've told you my prejudices already. Asking somebody, like asking on the NANOG list, is, I would say, a waste of time, because you get all the confederation people saying confederation, all the route reflector people saying route reflector. Exactly the same question if you ask, should I use OSPF or ISIS? So VJ Gills explained his transition, why he did the transition at AOL from OSPF to ISIS, and Dave Katz has done a presentation further back explaining the non-differences between OSPF and ISIS. So I'll leave it up to you, but it's generally a good idea, if you're using BGP today and it's still full mesh, to think of transitioning into something that's nice and scalable. One point about confederation, which I think is probably quite neat, it can actually ease the absorbing of other ISPs. I mean, I suppose this mattered more in 99, 2000, 2001, when people were going on spending sprees buying up ISPs. Well, I don't know about inside the ISP operational community how much visibility you had, but I had a lot of visibility of this sitting inside vendor land because we got endless questions of, oh, my ISP has been bought by X and we need to change the BGP, what do we do? And now the answer always seemed to be, well, just they're running a confederation, just join their confederation as a sub-AS, and that made it dead simple. And that's basically what everybody did. It actually made it really easy to do the transition. And of course, if you want to scale the sub-AS, you just simply use route reflector inside the sub-AS. It works beautifully. Okay, route refresh. That's pretty much should be mandatory these days. It's generally programming people's fingers to remember to do the proper clearing of the BGP session. Route reflectors or confederations, well, that's really the only way you're going to scale the iBGP mesh. Actually, these days I tend to recommend people just to do route reflectors from day one. I mean, most people who are starting building an ISP tend to have more than 1 or 2 routers. Even by the time you get your 3rd or 4th router, it's probably worth thinking about it because it will let you scale the network as you add more routers as you grow. Re-architecting the network 6 months or a year down the track is probably not such a wonderful idea. Certainly not a great experience when you've got other things to try and do. Okay, now I'm going to be a little bit controversial. This presentation over the years had, yeah, you got to do route flap damping because it was good. So look at the subtitle, Network Stability for the 90s, because that's what we believed then. Network instability for the 21st century, because there's enough evidence to suggest that these days. Why? Okay, well, for many years, route flap damping was strongly recommended good practice. Those of us who've been around in the early 90s knew the reasons why we had flap damping. Back in those days, it was basically before the common internet connection was a T1 circuit. Back in those days, people were still dialing in. And they got their Class C addresses from John Postel or whoever, and they dialed in, they announced the Class C, and then they hung up and they withdrew the Class C. And lots of people were doing this. And I was poor little ISP sitting in Europe watching all of these huge amounts of address space, well, coming from the US and from Europe as people dialed in, hung up, got the mail and so forth. And it was causing a huge amount of updates to what were really very punny router CPUs in those days. So flap damping was a good thing. A route flap is basically the going up and down of a path or a change in a BGP attribute. Okay, so BGP withdraw followed by an update. Well, in Cisco speak is a flap. In Juniper speak, it's 2 flaps. But anyway, that's a subtle difference. If your actual BGP session goes down, that's not considered a flap. It's only if you get the withdraw followed by update message. These flaps ripple through the entire internet, they waste CPU, and the whole idea of damping was to reduce the scope of the flap propagation. So the requirements was you want fast convergence for normal route changes, you want to use history to predict the future, so if a prefix was flapping lots, it's going to carry on flapping. Prefix is stable, it's likely to remain stable. You want to suppress oscillating routes, advertise the stable ones. RFC 2439 describes it all. How it works? Well, every implementation is similar to this, but in iOS, we add a penalty of 1,000 for each flap, so that gets attached to the prefix. One thing that is in the small print in the documentation, well, once it appeared in the documentation, was a change in attribute gets a penalty of 500. So even if you change an attribute, if you change the community on the prefix, hey, you get a flap. If the AS path on a prefix changes because somewhere else in the network had a change or for whatever reason, you hit it with a penalty of 500. And this is actually a serious problem. Exponentially decay the penalty, half-life determines decay rate, penalty goes above a suppress limit, you suppress the prefix. Once the penalty is decayed below a reuse limit, you then re-advertise it. Okay, picture is worth 1,000 words. That's basically what happens. Okay, so as time axis comes along the bottom there, prefix flaps. This is going to be really hard to do. Prefix flaps. It flaps, well, 3 times there. The penalty has gone above the suppress limit. Carries on flapping. Fix the problem. Get potential decay back down limit, and then the prefix is re-announced. So you've got this time in the middle here where the prefix is not actually advertised to any of the BGP speakers. So that way, if any big flaps came into your network, you would stop them from going any further. So that's what was basically coded about, I think it was about 1996, this was, or 95, it was probably coded, 95, 96, sometime around about then, and has been deployed in various forms in the network since then. It only applies to inbound announcements from eBGP peers. Alternative paths are still usable. So if a prefix flaps on a particular path, it's only that path that is suppressed. So alternative paths would still be usable. So if you get one path that's flapping an awful lot, it gets suppressed, you then use the other path as the backup. And you've got various ways of controlling it. You can change the half-life, reuse limit, suppress limit, the maximum suppress time. All these things were user configurable. The different implementations let you set various policy control with flap damping. You can have fixed damping. You can have variable damping. Apply to different prefixes, different prefix lengths, and so forth. So first implementations, okay, well, there were 95. I was almost right. Cisco was the first implementation out there. It was decided, or the ISP experience was that the Cisco defaults were too severe. I mean, how was Cisco to even know what the good defaults would even be? I mean, they had to write the code and then, well, we had to try something to see what would work. So basically, the RIPE routing working group had a look at some of this because it was biting probably European ISPs more than in North America, although it was some North American ISPs who helped with the initial working group recommendations. So they came out in RIPE 178 document. That was further refined in RIPE 210 and RIPE 229, so if you're interested in those historical docs, they're on the RIPE web pages. And that was an attempt to try and get some sanity into the different vendor defaults. So 178 tried to fix the Cisco defaults, and finishing with 229 where we had we had recommendations for variety of vendor equipment and what to do with, say, the .root server networks and so forth. But we've also found that many ISPs just simply switched on the vendor's default values without even thinking because, well, they downloaded the vendor's, this is what you need if you're running an ISP template, and they just dropped that onto the router, and then more often than not, it just came up with the standard damping values. And so the problems, well, I think this all really started with Abba Ahuja and Craig Leibovitz's early work on routing convergence, and they were knowing weird things happening because of ISPs implementing flap damping. Morley Mao carried on the work with her team. The route flap damping exacerbates internet routing convergence, so that was the oft-quoted document now that's looked at some of that and proposed some good solutions, which of course nobody's implemented at all. Tim Griffin has had a look at this. Randy Bush and others have had a look at it, again, sort of sideways from his Happy Packets work that he's been doing. So suddenly there were serious issues highlighted. So first problem was one path flaps. Well, BGP speakers pick the next best path and they announce that to all peers. The flap count is incremented, that's fine. Those peers see the change in best path, flap count implemented, because, well, the attributes change because the S-path attribute has changed, has it not? After a few hops, peers see multiple changes simply caused by a single flap. The prefix is suppressed. I didn't believe this when it was first presented to me a few years back. And then, of course, I was working with a lot of ISPs, mostly in Asia-Pac, with multi-homing. And what you do in multi-homing is, well, let's pop out a /24 and see if this helps with our load balancing. Pop out the /24. Nah, doesn't seem to make much difference. Withdraw /24. Have a look in half an hour. Wow, our /24 is there, but it's flapped 40 times. How could it possibly have done that when we only announced it once? So then it was like, oh, okay, so maybe there is something about this. You can go to Looking Glasses and see this sort of thing still happening even today. Maybe not quite so as dramatic as them, but you can certainly announce a /24, withdraw it, and you'll see it flapping 3, 4, 5, 10 times half an hour later. So that was the first issue. Different BGP implementations have different transit time for prefixes. Some hold on to the prefix for some time before advertising it. This was this minimum advertise timer type thing, which some implementations simply don't have. and others, well, they'll hold on to a prefix before they re-announce it. And that meant that if you announce a prefix, it was announced through the internet at different speeds. Well, guess what happens there? Again, routers see different paths. So this is a good path, and then, whoo, suddenly one appears from the other side. Ooh, that becomes the best path, and you get, again, change in path, change in attribute, and oscillations. So this race to the finish line just looks like flap damping, but it's a simple, innocent announcement of a prefix. So that was another major issue. So, well, the RIPE Routing Working Group has discussed this again, or more like it's been, the last 3 or 4 meetings been, Philip, have you written anything about this document yet? The joy of having co-authors, they can delegate. And so basically, we had a fair bit of input from various ISPs and other folks about what should be done, and the general consensus seems to be that flap damping as currently implemented by the vendors does more harm than good, especially in the examples. If you announce a single prefix and the fact that you can see it having flap just after a single announcement. So the advice is generally not to do it. We did a straw poll of ISPs at the RIPE meeting, and I think about 3 hands were put up who actually were doing flap damping. So that was quite interesting in itself. I mean, in my tours around Asia, I just found ISPs have put the default default flap damping that Cisco or Juniper or whatever have on the router, rather than using any of the recommendations anyway. So the general thing is, in its current form, not to do it. But again, I mean, we haven't just said, well, this is bad, full stop. Well, actually, now next step is to have a look and see how flap damping could actually be made better, more useful. Anyway, RIPE 378 covers all that if you're interested in reading up more about it. So that's generally hot off the press, because RIPE 378 was only published about a month ago. Okay, so that's flap damping, is generally try and avoid it, unless you really think it's going to benefit your network somehow. Right, I'm going to have a quick look at communities. I'm sort of a little bit behind and need to try and catch up as much as I can. BGP communities I consider another scaling technique for BGP. I mean, it's not really a scaling technique that people would recognize, but I recognized it as a scaling technique operationally. It made huge operational sense for our network because we didn't have to plan, as I was describing right at the start, we didn't have to plan maintenance outages just to announce customer address space to the internet. And that was a pretty big win for us. Prefixes are grouped into different classes or communities within the ISP network. Each community means a different thing and has a different result in the ISP network. So what do you do with them? You generally set communities at the edge of the ISP network. So there's the customer edge where you set customer prefix belonging to different communities depending on the services they've purchased. Okay? I mean, it's not just a case of, oh, well, we'll give you all access to everything on the internet. Certainly we found in the UK that some of our customers wanted access to the rest of Europe. Some people only wanted access to UK. Some people only wanted access to the links, the exchange point in the UK. Some people only wanted access to the US. We could offer all these things. Well, at least our salespeople offered all these things, so we had to come back and implement it. And, you know, it was a nice thing to sell because our competitors couldn't offer this sort of nice long shopping list of options. And I was like, yeah, Philip will go and implement this, no problem at all. So communities were a big win for that. I mean, trying to do this with prefix lists and so forth beforehand was pretty hard. And you can also use communities at the internet edge. So transit provider prefixes belong to different communities, different peers, prefixes in different communities, and so forth. That can also be pretty handy. So I've got some simple examples. The first one is at the customer edge. Here, suppose the ISP's got 3 connections to the internet. It's got an exchange point for your local peers, got private peering maybe with a local competitor, and your transit provider. And customers basically have the option of purchasing combinations of the above connections. Okay. So you could set aside communities. You could set aside community 100:2100, for example, for the exchange point connection, 100:2200 for the private peer connection, and well, customer who wants both of those, they get put in both communities. Customer who wants everything, well, you can set another community or just set nothing whatsoever. we actually set nothing whatsoever, which is why I've got it in this example like this. So you could do that. And then your customers, you know what each community means. So when you're doing your filtering at the edge of your network, you just announce these communities rather than having to worry about which prefixes should be going where. So it's like that. The customers come into the aggregation router. We set up the aggregation router, and then the border router is basically where you have all the community filters set up. The beauty is, as you add more customers, or as you add more prefixes that the customers are going to announce to you, maybe they've got better address space, maybe they've got their own address space from somewhere else, then it's just a simple case of adding it to the border router, and the rest of your network is set. You don't have to go and make any other changes. So it really makes things so much easier. And I probably haven't done a good job of explaining how easy it is, but I suppose it must have saved us substantial hours per week when we actually deploy communities like this, simply because we didn't have to run around so many different edge routers, updating filters and planning maintenances and so forth. The second example, you can set the communities at the internet edge. And this demonstrates how they might be used at the peering edge of an ISP network. ISP's got 4 types of BGP, well, relationships. I've called it peers here, but 4 BGP relationships. It could be with a customer, it could be with an exchange point peer, it could be a private peer, it could be a transit provider. Again, you can classify the prefixes into different communities. Okay, and then your customers can opt to receive any or all of the above. So this is selling the different services to your customers. So again, you could set community 100:3000 for any BGP customers, 100:3100 for IXP customers, private peer 100:3200, and somebody who wants the whole internet, well, just no community needed at all. Just give them everything. And again, setting this up, if your customer wants these particular accesses, then you just announce those particular communities towards them, rather than having to do any custom filters for them. And again, it simplifies configuration. You have one configuration pointing towards all your BGP speakers, rather than having to do a custom configuration per customers. Why did we do this? Well, we ended up having to do it because, as I was saying before, our sales were very good at selling new services. So they had new services pretty much for what the customers were requiring to do, and having some customers who wanted us purely for UK access. They were quite happy with the transit provider that gave them access to the US or to Europe, but they wanted us for UK access for whatever reason. And so we had to come up with a custom configuration. Then when the second one came along, the third and the fourth, and it was like, oh gosh, this is just getting hard. 4 custom configurations doesn't scale. So coming up with a community-based solution to try and do this made it substantially easier. Okay, so as I was saying, no need to create customized filters. Now, so those were the 2 examples of how you might go about using communities within your network. Even if you haven't quite figured out the filtering part, it might still be interesting to do the different classification. I mean, we added further classifications. We got the dial-up network and so forth, and as other types of services were added, web hosting and so forth, we put them all into different communities so that we could identify where the particular prefixes came from by community. And that was pretty handy for us. Now I've just plucked some examples off the net. ISPs also create communities to give customers bigger routing policy control. I spend more time this in the multi-homing tutorial than I do in this one, but it just gives you a general idea of some of the things that ISPs actually provide. Public policy is usually listed in the Internet Routing Registry. In fact, all these examples, they're in the IRR or in the ISP's public web pages where appropriate. And I'll just show them for examples. You probably can't see that one because it comes out pretty hard to see here. That's an example of what SprintLink actually does for AS1239. Again, it's on their web page. You can go and have a look at that. But I don't know if you can see it. If you this one here, the second one down, says if you send community is it 65001 colon something, it will do a single AS path prepend of 1239 towards AS something. Okay, so if you know who Sprint's AS peers are, then you can actually do a single AS path prepend of your address space towards that particular AS. So it lets you do fairly fine-tuned multi-homing for your network between Sprint's different peers. So it can be really powerful. But I mean, obviously it's got dangers as well. And also, for a service provider who's offering this facility, you've got to be aware that your customers can wedge your bandwidth without you really being aware of it. So you kind of got to watch what you do. So there are some examples from Sprint. You can get more from that URL, which, well, it worked the last time I looked at it. So another example, AAPT, which is an Australian ISP. They've got 6 communities offered to their customers to try and aid with their traffic engineering. So these are the examples here, probably easier to see. If you send 2764:2, they won't announce your prefix outside the point of presence you connect to. If you send them 2764:4, they will lower your local preference by 15, and so forth. Okay? So those are the sort of things. There's another one, 2764:7, only announced to customers, so they don't announce it outside their own network, so not to peers, not to international transits. Okay, so that's kind of thing that could be useful as well. Next one, MCI Europe, or whatever they're called these days. So there's Verizon Business Europe, or I don't know. Again, similar idea, AS702. So they let you send 702:80 will reduce the local preference or set local preference to 80. 702:120 will set local preference 120. If the default's 100, the first one lowers the local preference, the second one increases the local preference. So remember I was mentioning MED being sort of really in bad name these days. This is the alternative. You send 702:80, it's the same as increasing local pref if you're multi-home to them. 702:20 announced only to MCIs, ASs and customers. 702:30 keep within Europe. 702:1 do a single prepend. 702:2 do a dual prepend. 702:3 do a 3 times prepend. And those all came from what we did way back in the UK, so they were adopted for the European-wide network as well. And there are more examples of what they offer. BT Ignite. Well, that used to be Concert's European network, but it's now BT Ignite. Again, that's kept in RIPE's routing registry, so you can look this one up if you want. So they've got a very, very detailed and complex community thing. In fact, I think somebody tried to set all the communities once, and there were some implementations of BGP that couldn't handle more than 32 communities. Well, they didn't handle them very, very well, so they fell over, which wasn't too good, but it was because somebody tried to set all of BT Ignite's communities. But again, you can set various ones to the various peers. So if you say, for example, if you set 5400:1500 on your prefix towards them, they will not announce the prefix to any of their transits. Or if you send 5400:2500, they will do a single times prepend to all the transits. I mean, I've worked with a couple of BT Ignite customers, and I've played with these communities, and they certainly seem to do the job. But I think I'm probably more limited by the number of communities that I can actually set over what they support. It's a huge number. There's Carrier 1, that's another one, AS8918. No idea what happened to them, but their object is still in the RIPE database. So there's some more examples of communities that can be set by customers to do things towards their transits and their peers. So if you set 8918:2020 on your prefix towards them, they won't announce it to Teleglobe, for example. 3356, level 3, really, really complex one. If you print out the whole thing, it goes on and on. I'm sure it's useful for some things. I mean, you see the standard ones near the bottom there, 3356, 3356:70, set local pref to 70. 80 and 90. Those are the RFC 1998 values of communities that, well, basically Internet MCI documented many, many years ago, not long after communities actually came out. That's what they did, and it's kind of an unwritten default set of communities that people use. But level 3 support loads of other ones as well. I don't know if they do in the US, but this is on certainly in Europe on the routing registry hosted by RIPE. There's loads of things that you can actually do there as well. Okay, so I went through that pretty quickly. It gives you some examples of what ISPs are using communities for. Next one, final bit, which I've got to try and finish in 3/4 of an hour, is deploying BGP in an ISP network. So, right, we've learned all about BGP, I hope. So how do we actually go about deploying it? First thing I want to do is really just remind about IGP and IBGP. There's still a belief out there in the net that IGP can carry everything and anything going. And, well, that's probably true. If you throw enough CPU at your routers, you can make it do all sorts of magic things with your IGP. But the point is, it's still bad design. You're not going to get a standard everyday road car to take part in any road race of any description. And I suppose Formula 1 Grand Prix doesn't mean so much here as it does elsewhere in the world, but you know, in the Indy, whatever it is, it doesn't make sense just taking a standard road car doing that. Sure, if you put a big enough engine and turbocharger and supercharger and nitrous, whatever, you can make it go fast, but it's still not going to do it. So it's better to use the properly designed tool for this. So OSPF is an interior routing protocol for a particular reason. Okay, they're used for carrying your infrastructure addresses. So if your point-to-point link addresses between your routers, the actual loopbacks on your routers, and that is about it. Your customers are not your infrastructure. Your web servers are not your infrastructure. All your hosting LANs and all that stuff is not your infrastructure. Okay, your infrastructure, it's your routing infrastructure, it's your routers, the point-to-point links that connect them, and the loopback interfaces. Don't put internet prefixes in there. Don't put your customer prefixes or anything else. Because the design goal is really to try and minimize the number of prefixes in your IGP. Okay, that's the aim. The fewer the prefixes, the faster the Dijkstra algorithm will work, the faster the OSPF or ISIS will converge. It's just a simple fact of life. Yes, you can make it converge faster by putting a bigger CPU, but that's not really solving the problem. BGP, as I said, is used in 2 places. It's used inside your network, IBGP, and it's used between autonomous systems, EBGP. IBGP is where you carry all the internet prefixes and your customer prefixes and all the hosting LANs and everything else that you don't put into your IGP. EBGP is used to exchange prefixes with other ASs, implement your routing policy. Okay, that's the simple divide. Reminder of the picture, that's what it's like. IGP lets your routers find each other. IBGP, you transport all your prefixes across your backbone. EBGP lets you exchange prefixes with other autonomous systems. Don't distribute BGP into OSPF or ISIS. I mean, you can try and do it if you want. 190,000 prefixes will probably go quite nicely into OSPF if you've got plenty of memory and plenty of CPU. I don't hold that much hope for your backbone working too well. Don't distribute IGP routes into BGP. IGP generally changes very, very quickly and wants to change, well, often and quickly. BGP is the slow, lumbering giant, as I like to see it. And, well, it doesn't take kindly to being prodded every few seconds as things change in the network. So it's probably not going to be too useful trying to distribute OSPF or ISIS into BGP. Don't use IGP to carry customer prefixes. It may work fine for the first 100 or 200 customers. When you've got 10,000 customers, it means you've got 10,000 prefixes in OSPF, and you've run into another scaling problem. Okay, suffice to say, your network won't scale if you try and do any of these. So, putting prefixes into IBGP. Well, firstly, don't ever use an IGP. Did I say that already? I think so. People still don't get it. I help out in so many deploying networks, and they still think, yeah, well, put all customers into OSPF. Yeah, well, we've only got 20 customers now. It's not going to be a problem for a year or so. Somebody else can solve the problem. And it's, well, yeah, that's fine, but you've got all the other side effects as well. What to do is point a static route to the customer interface and get the network into the BGP process directly. There's no need to have it in OSPF at all. Aggregation. Aggregation. Aggregation means announcing the address block that you've received from the registry, or indeed from your upstream ISP, to the other autonomous systems connected to your network. Because the registries give you an address block. They don't give you 32 Class Cs. But still, you'd be amazed at the amount of emails I get saying, ooh, I've got 16 Class Cs from APNIC, or 16 Class Cs from RIPE-NCC. And I was like, wow, really? APNIC never ever handed out Class Cs ever in their lives. And so it's like quite an interesting concept. So, and I point out to people that Class A's, B's, and C's disappeared in 1993 when we all moved over to the classless internet, and well, there we go. So, sub-prefixes of this aggregate may be used inside the ISP network. There's no problem. IBGP can carry hundreds of thousands of prefixes if you want to, because it's inside your network. It doesn't matter. Right? Your IBGP is the load carrier. It can be announced to other ASs as well to aid with multi-homing. That's traffic engineering. Okay, it's the original traffic engineering. If you need to leak some sub-prefixes to your neighbors to let you do load balancing over multiple links. I think that's accepted practice. Whether it's good practice or not is another issue, but it's accepted practice because that's the only way it works at the moment. Unfortunately, too many people are still thinking about Class Cs, and Bs for that matter, resulting in a proliferation of /24s in the Internet Routing Table. We'll see more about that in a bit. Okay, address block should be announced to the Internet as an aggregate. So if you get your /20 or 21 or whatever you get from Aaron or whoever, then announce it as that. Sub-prefixes of an address block should not be announced unless there's special circumstances. More later, as in next NANOG, if I'm asked back. Aggregate should be generated internally, not on the network borders. Why? Well, I don't have anything explaining that. But if you don't generate the aggregate internally, but you generate on your border router, well, my example, we started off UK ISP. We had our border router sitting in Washington at May East. We generated our aggregate there. Transatlantic link broke. We still generated our aggregate at May East. We couldn't get access to our router at May East. We had to phone somebody up and get them to switch it off. Not such a wonderful idea. So don't generate on the border. Try and generate somewhere inside the network. So at least if your border router gets cut off for whatever reason, if it's remote, then you don't end up with some panic maintenance. ISPs who don't and won't aggregate and are held in poor regard by community. I don't know if that's true anymore or not. Some people react adversely to the CIDR report and so forth, or my own routing report when they appear, but then again other ISPs go, hey, look, I'm #1 on the CIDR report. I must be big. So, I don't know. Registries publish the minimum allocation size. That's anything from, or it should be a /21 to /22, depending on the registry. There's no real reason to see anything longer than a /22 in the internet, but there are 102,000 /24s today, which is quite a few. And no, we can't blame them all on 192. That's like a standard thing. Oh, well, but it's all those Class Cs that were handed out way back before. I have news for those people. There are only 5,500 Class Cs that were, well, left in the routing table from 192. And everything else contributes to the 102,000 that are out there. So here's an aggregation example. Customer's got /23 network, for example, signed from AS100/19. AS100 is announcing their aggregate because they're a good ISP. Customer link goes down, they withdraw the /23 for whatever reason. /19 is being announced. That's it. Nobody sees that anything has changed. If anybody tries to get access to that customer network, well, they're just seen as traffic stops at their ISP. Oh, well, they must be down. Something's wrong. Customer link returns. They switch the router back on next day after going home. The /23 becomes visible again. They've got connectivity immediately to the internet because the ISP is announcing the /19, and the internet can see them because the ISP is announcing the /19. So it just works. Like you switch it on, like you switch the lights on, and they come on. Switch the lights off, they go off. That's how it should work. And that's one of the big advantages of announcing an aggregate, because you're always present, or your network is always present on the internet. And so the customer's got this quality of service perception. What about this case? ISPs not doing any aggregation at all. Present this example a few times, and I've still got people saying, what, you mean there's still people who don't announce an aggregate? Oh yes, there are a large number of people who don't announce any aggregate whatsoever. There are a large number of ISPs who simply think that announcing the IBGP to the internet is just fine. Well, it's not. IBGP is internal. eBGP is all about announcing aggregates and traffic engineering prefixes, in my book. So, this is an example. Customer leaks his IBGP to the internet. Customer link goes down. /23 is withdrawn from AS100's IBGP. That withdrawal gets announced to AS100's upstreams and their upstreams and goes through all 22,500 autonomous systems in the internet, assuming they all carry the full internet routing table. So every single router that participates in the full routing table sees this withdrawal. Customer link returns, he comes back to the office next morning, switches his router on. /23 is now visible, ISP announces it. Different propagation delays, different filters, different flap dumping policies, different everything. Internet may take 10 to 20 minutes to become visible. Customer phones up and says, oi, where's my internet? ISP says, I don't know, it works for me. I've heard all that before, but that's the issue. It's like you switch the light on and it sort of glows a little bit, and it gradually gets brighter over the next half hour. Is that what you want? Well, some people are perfectly happy with that. Some ISPs are perfectly happy delivering that sort of service, but it's not how it's meant to be. So that's the difference. Good example is what everybody should be doing. And I just find it amazing that people are still not announcing their aggregate. I get all sorts of weird excuses given for not doing so. Won't waste the time here with those. But basically, internet stability reduces size of routing table, reduces the routing churn, improves internet quality of service. Why don't people do this? They blame lack of knowledge, lack of training courses. Right, go download my tutorial from the NANOG website. I've only been doing it for 3-4 years now, so it can hardly be for lack of saying so. I suspect it's laziness. Just can't be bothered. Internet routing table, well, it's not quite today, but I didn't have a chance to update these numbers, but February 2006, it's only marginally short of what it is today. So I was seeing 188,000 prefixes. It's just short of 190,000 now. That's the routing table entry. One thing that I do in my little analysis work, I actually do the aggregation for ISPs that they could have done. And if I do the aggregation, I lose 84,000 prefixes from the routing table, just like that. Okay, that's just doing aggregation, which is quite extraordinary. If I look at the number of unique prefixes in the internet, I can reduce that a bit further, another 12,000 down, which is what you'd expect. This is more traffic engineering type of thing, or prefixes being handed out to customers and so forth. Prefix is smaller than the registry allocation size. While the registry has published the minimum allocation size, not only the 5 RIRs, also the IANA blocks and so forth. So if I count all those prefixes, the 93,000 prefixes smaller than the registry's minimum allocation. /24 is 102,000, 5,700 come from 192/8, 22,000-ish ASs in use. The new swamp, well, people used to call swamp space areas of poor aggregation. I mean, certainly when you're in the internet in 93, 94, 95, we all were talking about swamp space. The 192/8 address block was always the swamp space because it was no aggregation. Because, of course, all those prefixes were handed out as /24s, and there was a major effort to try and get ISPs who got multiple 24s to aggregate them. And that work was pretty successful, I think. But no, the new swamp is, well, creeping across the regional internet registry space, but also some of the legacy space. So people who formerly got Class Bs and Class As are now slicing and dicing just for fun as well. So that's the new swamp. The old swamp was probably a nice small swamp that we understood. The new swamp is everywhere. So if we wind the clock back, February 1999, I first did this presentation, so I still have the numbers. Well, if we can look at some of those. So 192/8 was 6,300 prefixes, more or less. So that's still quite a lot. 193 and 194 was seeing about 2,500 prefixes or so, for example. 198 is just a disaster area. That was 4,000 then. And a lot of the other blocks were still filling up and they weren't quite full. But that was back February 99, when the internet was definitely going through massive, rapid growth. If we look at, well, February 2006, well, let's see. Look what's happened to 193. Oops, where'd the pointer go? That's the pointer. 193 has gone up to, where is it? There. It's gone up to just over 5,000. It's gone up to over 5,000 from, what was it? It was 2,300. Just like that. I mean, why? 193 has been fully fully allocated by the RIPE NCC back in, I think they filled it up about 97 or something. So since then, people have decided, oh, well, let's chop it up into smaller pieces for reasons I'm not particularly clear about. Look at 202 and 203. Almost 10,000 prefixes just from those /8s. That's scary. 200 is pretty bad. 209 is pretty bad. 216 is almost heading for 7,000. We look down at the bottom, 66, where is it? 66/8 is, yeah, over 6,000. So there's a general trend to heading to about 6,000 or 7,000 prefixes. So these are the address blocks that are fully allocated. What about all the ones that are not fully allocated yet? And it starts getting really alarming. So that's just the general growth. The registry blocks contribute about 88% of the internet routing table today, as they did in 99, interesting enough. So RIR space showing creeping deaggregation. So RIR block is averaging about 4,000 prefixes once they're fully allocated. And then, of course, they seem to disintegrate after that. So if the existing 70/8s that the RIRs have, that will cause 280,000 prefixes in the internet routing table. Okay, so you can expect that. That's not a prediction. This is what will happen. What about the remaining 62/8s? Well, by the time they're all used up and the 70 registry /8s all used up, well, at 4,000 prefixes per /8, 500,000, 6,000 prefixes per /8, 800,000. Is this a prediction? No, this is what's going to happen. So when it will happen? Well, when are we going to run out of V4? Depends whose model you listen to. But that's the sort of size of routing table that you have to be aware of. One thing, if those of you on the NANOG list will have noticed, Jeff Houston started posting a BGP update report as well. So this combined with the BGP update storms that we seem to start getting on the net, people are going to have to start buying really big routers very, very soon, I fear. I'm not trying to sell routers, I'm just warning people that big routers are going to be needed to try and handle the full table. Rest of address space is showing similar deaggregation. Main justifications when you ask people is, oh, well, we're doing traffic engineering. But when you actually do the analysis, it doesn't stack up. Traffic engineering is probably about 10% of the deaggregation. The rest of it is, ooh, I'll leak my IBGP to the internet because, well, I don't know, I think it's a good idea. And IBGP is just BGP anyway, what's the difference? So that's how I justify at the start when I say, I try and tell people that IBGP is different from eBGP. IBGP is what runs inside, eBGP is what you tell the world about. They are different. Looking at, well, BGP report, this is Jeff Houston's work. 180,000 announcements when I took these numbers, that was sometime last year. Doing aggregation, including full AS path info, 35% saving is possible. So you can really, if people just did the aggregation, 35% of the internet routing table would disappear, just like that. Pardon me. If we aggregate by origin AS, in other words, ignoring the traffic engineering, 8% saving. So 8% is caused by traffic engineering. And the rest is whatever. So, anyway, moving onwards. CIDR report, as I say, the weekly report is posted to the NANOG mailing list. If you haven't ever looked at the website, I'd encourage you to do that. You can put your own AS number in there, and it will tell you how good your aggregation is. So it's changed lots from the days when Tony Bates started it off as a means of trying to encourage people to migrate from encourage people to aggregate, because it was intended to encourage people to aggregate the 192 address space. And those of us who had 193 space but were announcing it as in classful pieces. So it was encouraging people to to aggregate, but it's, well, got a new life now to try and encourage people not to deaggregate. So it has the website. You can say it's a tool. There's graphs you can click on, do all sorts of things. You can find out what your AS is doing. You can look at your address space and so forth. It lists the top 30 service providers who could do better at aggregating. Sad thing is, some ISPs use it as a positive marketing tool, saying, hey, we're number 3 in the CIDR report. We're good. No, you're not. You're number 3 worst. Well, that's what Jeff and I would certainly like to think, and I hope other people would think that as well. So as I say, also computes the size of the routing table, assuming ISPs performed optimal aggregation. Say, stick your AS number in there, and it will tell you what you could do. So, example of what the page is. I really don't have time. You can go to the website and you can pick up all these things. I'm not going to embarrass anybody, but you know who the top 30 are. So, graphs of the different aggregation potential. The top line is the internet routing table in the last few years. The next one down is basically aggregating, but including all the AS path info. And the purple one here is aggregating by the origin AS, so we ignore the AS path after that. And various others that you can do that are even so on. You go to Jeff's website to get the full data of this. So we are certainly watching. Anyway, if I haven't made it clear, 35% saving the routing table is quite feasible. By the time all V4 is used up, well, 35% saving on 900,000 prefixes, well, you know, that's 300,000 prefixes. That's pretty attractive. Unless you're quite happy to give all your hard-earned money to the vendors to build you even bigger, faster routers. And I'm not going to complain about that. Well, if it makes the share price go up at least. Sorry, I didn't say that. Right. I'm trying to encourage people to aggregate and not spend money just throwing more memory and CPU at the problem. And it's the same as putting the standard road car into the Indy 500 or something. It's, you know, bolting on extra features just to make it go that bit faster. It shouldn't be necessary with a bit of decent design. Okay, receiving prefixes. 3 scenarios for receiving prefixes from other ASs. So from your customer who's talking BGP to you, peer talking BGP, and the upstream or transit provider. And each one's got different filtering requirements and needs to be considered differently. So from your customers, you only want to receive the address space that you've actually assigned or allocated to them, or that they can prove is theirs. You don't just accept any old rubbish because, well, they announce any old rubbish to you. That's how spammers and other free marketeers have their success. They announce garbage that the upstream ISP is quite happy to accept because the upstream ISP only cares about the dollars and not about the success of the internet that they're part of. If the ISP is assigned address space to its customer, then the customer is entitled to announce it back to the ISP. That's reasonable. If the ISP is not assigned address space, then actually check up who owns the address space. Whois tools are there. I noticed on the latest Linux, the Whois tool there seems to be wonderfully enhanced. That goes asking all sorts of Whois servers all over the place to actually let you know what address, who actually has the address space. But for example, look up a Whois, and if it's not listed on one particular registry, well, check around all the other ones. And if none of the 5 know about it, chances are it's not actually assigned to anybody. So here's just one useless example. I looked up APNIC/24 that they use in Brisbane, and, well, there it is. It's registered APNIC, so they're allowed to announce it. Here's another one. This is provide aggregatable address space, so the PA address space. In other words, it's been given to the ISP by the registry, and the ISP has further handed it on to the customer for the use of the customer while the customer needs it. So that's one particular example. So if these people turned up to you saying, hey, give us connectivity and this is our address block, you would look it up, you get this answer, and you say, oh, hang about, but it's such and such as address space. Oh, yeah, but they said we could have it. Then you start getting suspicious and worried and start doing your checks. Okay. But you'd be surprised how many people say, oh, did they? Oh, yeah, okay, I'll announce it. It just happens so often. A peer is an ISP with whom you agree to exchange prefixes. You originate into the internet routing table. Okay. So that's fairly straightforward. So whatever they originate, you accept. Whatever you originate, they accept, hopefully. Okay, so you agree what each will announce to the other, so you can agree by email or whatever, the documentation you exchange when you set up the initial connection, or use something like the Internet Routing Registry. Internet Routing Registry lets you document what you're going to announce to particular peers. You've got the IRR toolset, which lets you automatically build or manually build router configurations, so that you can make the job of managing the peerings a lot easier. Upstream, a transit provider is an ISP who you pay to give you transit to the whole Internet. Do you receive the whole Internet routing table from them? Well, you can if you want to. There's no need to, because a default route is just as good. A default route says, I know how to get to the whole Internet. So why send 190,000 prefixes to somebody when a default route does exactly the same thing? Maybe if your customer wants 190,000 prefixes, that's fine. Or as Sean Duran has said many years ago, charge them money for it, because it costs you infrastructure to carry 190,000 prefixes on your aggregation router, so make the customer pay. If he wants the privilege, then he can pay for it. If it's necessary to receive prefixes from any provider, be careful. There's some that you don't really want to see. You don't want to see private addresses, RFC 1918, so network 10, 192.168 and 172.16. RFC 3330 actually documents special use addresses. So some of these you definitely don't want to see on the Internet. Don't accept your own prefixes. I mean, that's kind of obvious. If you've ever suffered a DOS attack from somebody else announcing your own prefix, own address block as /24s, you very, very quickly don't accept your own prefixes from anywhere else. Don't accept the default route unless you need it. There's some people who seem to enjoy announcing the default route to the Internet. Guess they've got nothing better for the network to do. Don't accept prefixes longer than /24. Well, that's a contentious one. It seems to be a kind of industry burnt-in default without really much thought about it anymore, because the smallest assigned address space ever was a /24, as in a Class C, even though the registries have handed out smaller chunks than that. But there seem to be a lot of people who have filtered /24s. The best place to go to is actually Rob Thomas's Project Gumri website. He's got a list of bogons on there. He's actually got a BGP feed that he can provide to you, and then you can keep your filters updated like that. So you don't need to sort of set up filters that are valid one day and then leave them on your network, and then 5 years later you've got all the people from Africa saying, hey, we can't get access to CNN.com because, or some example like that. Okay, so using a live Bogon BGP feed is probably a pretty good idea if you want to do this filtering from your network. John wants to say something, or not? Oh, I see. Yeah. I say I can tell stories. I can tell stories. I mean, the last problem was in Africa. It was Net 41 as an ISP who got an allocation out of 41, and he couldn't get connectivity to half of Europe and half of US. And it was, well, caused by a filter of 41/8 being set up a long, long time ago, and people had forgotten. So, getting a feed from Rob is probably a really good idea. Receiving prefixes, pay attention to prefixes received from customers, peers, transit providers. It's just, just the general good stuff to do. Be a good citizen. Preparing the network. I'm going to go through, I've got two examples here. I'm only going to go through one because, well, the second one is similar to the first. Want to deploy BGP across the network before we try multi-home. BGP will be used, therefore an AS number is needed. Multi-homing to different ISPs, you need a public AS number. So you get that from the upstream ISP if they're a registry member. Join the registry yourself. I definitely recommend that one because you get your own address space as well. And having your own address space as a service provider is a lot easier to make a lot of these things work properly. I know there's some organizations that probably don't fall in the minimum qualifications. Each registry region seems to have slightly different minimum qualifications to get address space, which is a bit unfortunate. But get an AS number, get your own AS number, get your own address space, and then a whole lot of BGP world becomes so much simpler. So the initial assumptions, BGP is not running in the network at all. We've got a single statically routed connection to the upstream. Network is not running any IGP at all. So what we're going to try and do is figure out what we've got to do to our statically routed network to go and deploy an IGP and BGP so that we can actually talk BGP to our upstreams. So first example, which is what I'll go through, pick your IGP. So you send your email to the NANOG list and say, hey, I'm going to deploy an IGP. Which one should I use? And be prepared for the 101 emails that will follow afterwards, or email from the mail admin team saying, can you not just read the FAQs or something? So pick your IGP, assign loopback interfaces and your /32 addresses for the loopbacks for each router, which will run the IGP, because, well, loopback is used for the OSPF, used by your OSPF, certainly in Cisco. Use it for the BGP router ID anchor, also in Cisco iOS. Used for iBGP, if we're going to set up the iBGP mesh, you run it between the loopbacks, and for originating prefixes. So we deploy IGP. For example, I picked OSPF because that's the one I've used all my years. Notice that IGP can generally be deployed without impacting the existing static routing. Again, static routes tend to have a very, very low distance, so distance of 1, for example, in iOS, whereas OSPF is distance 110. So you can deploy OSPF distance 110, and static routes are always going to override it. So it's rarely going to be a problem. You can deploy OSPF, boom, just like that. And all these people who have helped don't never believe me, and I go and do it for them, they say, oh, it just works. Well, yes, because of the distance, the protocol distances. Be prudent when you're deploying it. Put the router loopbacks in there, put the WAN point-to-point links in there, and in fact, any link that you're going to run a dynamic routing protocol over. So for things like hosting LAN or where your name servers go and so forth, don't put that into OSPF. There's no point. You're not going to run any dynamic routing over those LANs. Try and do any address summarization if you can for OSPF. If you're using multiple areas, I know that can be hard for some networks, but generally just saying, think about your IGP addressing plan, just to try and keep it simple. Routes which don't go into the IGP include dynamic assignment pools, so your DSL, cable, dial, wireless, all those dynamic pools, they don't go into IGP. Customer point-to-point link addressing. Okay, it's a point-to-point link address that you use going from your aggregation router to your customer. Okay, some people use unnumbered interfaces, other people use this BGP next hop self thing. Static or hosting LANs don't go in IGP. Customer assigned addresses don't go there. In fact, anything else not listed in the previous slide. Okay. Second step is to configure the local network to use iBGP. And this is always the next question. People seem to think that BGP means a big router. And you know, I don't know, I'm getting close to getting tired of contradicting all these people who post on public mailing lists saying, oh, well, you can only run BGP and it's a divide in the world. The third world is disadvantaged because they can't run BGP because they need to buy a Cisco CRS1 to do it. And it's a load of nonsense. You can run BGP on, well, we were running BGP at AFNOG on a router this size. Okay, it's the little Secrets box running FreeBSD. We're running BGP. It can do it, okay? The size of router has nothing to do with the ability to run BGP, and that's pretty important. But aside from that, people still seem to freak out about it, and it's a major issue. Where you run it, you need to run it on all routers that are going to be in the transit path. For example, if the link between A and B here disappears, the link between A and B there disappears, well, what's going to happen? D and C are going to be in the transit path, because the iBGP is going to carry on going. It doesn't care about your infrastructure. What about if the link between A and D disappears? Well, A, F, E, D, C, B are going to be the transit path between routers A and router B. Okay, so all these routers will need to run iBGP of some description so that if you have any break in the network, at least the network knows how to get to the edge. Whereas this example, C, E, and F don't need to run iBGP if you don't want to. But as I always say, there's not really many routers these days that can't run some description of BGP. I mean, if your vendor still sells you stuff that can't do BGP, go and beat on them to make it do it. It shouldn't be that hard. And even if it doesn't, in this case, it could be some aggregation boxes. C, E, and F, you point a static route for the address block that it is handling from the router D, and everything is just handled quite nicely like that. Typical service provider network, well, a large one will have 3 layers. You've got your core, usually the transit path, the backbone, the distribution layer, which is the middle where you aggregate regional points of presence into the core. Aggregation layer, that's where your point of presence is, where you connect the customers to your backbone. Aggregation layer, I say IBGP is optional. My recommendation is always to try and run IBGP there if possible, because it just makes things easier. People never believe me, but by the time it's been deployed on the network, they all tend to agree after 6 months of operation, because they add another router and it's just boom, one more router has to be added in, rather than thinking of a myriad of static routes and how to handle the IGP and so forth. Full routing is not needed unless customers want the full table, and if customers want the full table, make sure they pay for it, at least pay for it in terms that they can fund your infrastructure. Partial routing is cheaper and easier, so in the core of your network you may want full routing. When the core routers advertise IBGP prefixes out to the edge, you just put a filter. In fact, if you're using communities, it becomes amazingly easy, because it says only advertise my communities, my networks, to the edge. Don't advertise internet-learned prefixes. Many aggregation devices can't run IBGP, I accept, so static routes from the distribution devices for the address pools, and then use IGP for best exit. Distribution layer usually runs IBGP, partial or full routing. Doesn't have to run it, but I find that it's harder if you don't run IBGP at the distribution layer. As for the core of the network, it's usually the transit path. IBGP is pretty much mandatory here. Full routes or partial routes, depends whether you're going to be an internet transit provider or you're an internet edge. Transit provider, I mean you're providing transit to other autonomous systems. Edge means you're just connecting standard non-BGP speaking customers to the net. So you decide on your best IBGP policy, full routes everywhere, or full routes or somewhere, partial elsewhere, and so forth. Pick your scaling technique. What BGP communities are you going to use? Start thinking about it then. Don't make it too complicated. Just set up some nice simple categories. Obviously, you're going to deploy route reflectors for scaling from day one. And then are you going to use things like, well, iOS peer groups, peer templates, or any other templating capability your vendor implementation has? Then you deploy IBGP. So you introduce the IBGP mesh on the chosen routers. Make sure the IBGP distance is greater than IGP and the static routes, which it usually is. Install the customer prefix into IBGP. It should just work, just happens because the protocol distances are right. Now you remove the static routing, and that's where it all becomes critical. So you don't just go around the whole network and yank out all the static routing. Pick on one router with friendly customers. Maybe it's your staff's router that they connect to when they work from home. That's a good test, because A, can either encourage them to come to the office, or B, can encourage them to let you know there's something wrong. So start on something like that first, see how it works. If you're happy that it works, then move on, start picking on your customers. Friendly ones first, and finish with the unfriendly ones, and so forth. So actually it's pretty easy to do. Given I'm helping a lot of ISPs set up multi-homing, we go through these steps, and people really can't believe that it is as straightforward as this. I suppose because I've done it lots of times, it's just like, yeah, do this, and this. For a newcomer to it, it's still pretty scary trying to do some of this stuff, and you probably won't do this work in 30 minutes like I would do it. You would do it over 30 days or something, in very careful stages. Okay, I'll just jump over these because I really don't have any time left. So they're not flag day steps. I'm suggesting try step 1, week 1, step 2, week 2, step 3, week 3, and so forth. You do it in gentle stages through the network, and be very aware of anything that might actually go wrong. I'll skip through this because I don't have time. Don't want you to miss the beer and gear, so I've got about 15 slides left. Just want to finish off with some configuration tips. Just going through like templates, passwords, some more tricks, and so forth. First thing, I think the loopback interface is pretty useful. And I haven't checked other implementations, but certainly running IBGP between the loopbacks on the router means that you protect your infrastructure from any actual problems with the network. So running IBGP between loopbacks is a really good idea. Make sure well, the IGP carries the loopback /32. There's no point giving a loopback interface any other address space. But still, you know, lots of people seem to give Class Cs to loopbacks. It's like, okay. So what are all the hosts you're going to get connected to your loopback interface? What about the demarcation networks? Well, you can use your unnumbered interfaces maybe, but we use that quite extensively at UUNet, which worked fine for us. It saved us loads of address space, and the rep NCC were happy with us. Other people don't like it because it makes it really hard to try and manage your customer point-to-point connections and your customer connections in general. Other people just use standard addressing for the point-to-point links, but use this next hop self thing in IBGP. What that does, rather than the external prefix having the external point-to-point link as the next hop address, it actually used the router's local router ID or loopback interface as the next hop. And that meant saving you carrying all the point-to-point link addresses on the external side of your network round in your IGP. So you've got 10,000 customers, you don't have 10,000 external point-to-point links to carry. So that's definitely worth doing. You can even think about carrying the demarcation /30s in the IBGP if you really want to carry the /30s. Some people do monitoring for the customer connections. You can carry the /30s. Some people do that, but if you do, please don't leak it to the internet, as some people do. Basic idea is to keep the demarcation nets out of the IGP. Next hop self, so that's basically resetting the external next hop to being that of the local router. I generally recommend that as any IBGP template these days because it just makes things much easier. So templates, well, again, I do advert for Rob Thomas's site. The Project Cymru has got the BGP templates as well as loads of other useful templates. It's worth, I mean, his one is highly detailed and it certainly supports Cisco and Juniper. I don't know about other implementations. So it's got standard things that you should consider for your BGP sessions. It's well worth having a look at. Obviously, don't just cut and paste it and use it as is. Think about why each of the entries have been put in there, and you may want to use some of them, you may not want to use some of them. It's up to you. But have a look at some of the more standard things that have been done on the net. So an example IBGP template, run the IBGP between the loopbacks, use next hop self, always send communities in IBGP, and it's just annoying that iOS doesn't have this by default. Other implementations at least do have it by default. That way you avoid accidents happening. If your customer sends you a no export community, you're not going to start leaking his prefix to the internet. At least that protects against this accident. Hardwire BGP to version 4. You never know. You may get a joker who comes along and tries to set up a BGP version 5 with you. Or you may get somebody who still tries to run BGP version 3. You never know. Passwords in the IBGP session. Well, that was talked about in the session this morning. Some people use passwords. Some people don't, but I still think it's pretty necessary. It's the best of what we've got at the moment until we get something better. BGP template for eBGP, BGP damping. I really think this is a bad idea these days. You find a lot of the so-called tier 1 ISPs don't do this anymore. In fact, I've stopped doing it years ago. In fact, not many people do BGP damping at all. So don't use it unless you understand the impact, and definitely don't use the vendor defaults without thinking, because the vendor defaults are more severe than the others. Oh, remove private ASs from any BGP announcements. Private ASs should not appear on the public internet. Look at my routing report. Well, there are always 3 that appear, and they're the same usual suspects that appeared for the last few years. Obviously, nobody really cares too much about it, otherwise they would have gone by now. So just strip out all private ASs from any eBGP announcements. Use extensive filters. The way I did the filtering was I had a prefix filter to filter prefixes from neighbors. I also used an AS path filter to back up the prefix filter because, well, you know, I've been burnt with prefix filter being blown away or misconfigured, and, well, more prefixes coming in than should have. So AS path filter to back up the prefix filter is pretty useful. I always try and keep policy language separate from the filtering. I know some people have great fun coming up with really, really complicated policy language on routers. I'm afraid I'm a keep it simple person, and I like keeping the policy language for just policy and not doing more things. And the password on the eBGP session as well. Maximum prefix tracking can be useful, especially nowadays where it's got slightly more useful than it was in the early days. Router can warn you of the sudden increases in the BGP table size, and it can bring down the BGP session if you really want this, or it can just send you warnings. If you expect to get 10,000 prefixes from your peer, and you suddenly get 190,000 prefixes, and your router's only got 16 meg of RAM, well, at least you're protected from that problem. You get a warning. Log any of the BGP state changes, and keep an eye on the logs, because the router will tell you if things go wrong. It's probably worth having a look at those. The BGP administrative distance. I've been burnt by this one as well. Make sure the BGP administrative distance is larger than that of your IGP. External BGP by default on Cisco's has admin distance of 20. OSPF is 110. You learn a prefix from the outside world that's known in your OSPF. Which one takes priority? eBGP? Bad news. Really bad news. In fact, your network stops functioning. Getting out of that one, well, when I had to get out of that one, wasn't pretty. So, for goodness sake, make sure your eBGP and iBGP distances are greater than your IGP, and then you won't end up cooking your network. What else? Oh yes, some BGP implementations have problems with long AS paths because, well, when they were written, people didn't think the internet would be more than 5 or 10 ASs deep, so that's all they allowed for. And, well, actually, the AS path, the actual thing could only be accommodated within basically 256 ASs. So when you got the 257th AS, it started overwriting other parts of the router memory, and things went very horrible. So you could, suddenly iOS has got a way of limiting the number of length of the AS path, so you basically drop a prefix if the AS path is longer than something you set. Even using AS path prepends, it's not normal to see more than 20 ASs in a typical AS path in the internet today. And that's something I've added to my own routing report. The longest AS path prepend, which I think is about 16 ASs at the moment. So the largest is usually about 16 to 20, including prepends. The average depth of the internet is 5 ASs. It's not deep at all. Okay, so why we see things 30, 40, and so forth is always a mystery. Of course, some ISPs seem to think that if you make the AS path really long, it will override local preference. I haven't seen that one in the BGP spec, but you'd be amazed at the amount of people who believe that. Some announcements have ridiculous lengths. So this is one example from the IPv6 space. This was really, really long, really long. My cold is making it difficult to pronounce some things. So again, if your implementation supports it, consider limiting the AS path. I mean, I generally stick that in as a template. This one's interesting, the BGP TTL hack, RFC 3682, where the neighbor will set the TTL to be 255. So the local router is told to expect incoming BGP packets having TTL 254, which is quite interesting, which means that nobody, apart from the directly attached devices, can send BGP packets arriving with TTL 254. So if a miscreant, which way did the pointer go? If a miscreant tries to send a BGP packet with TTL 255, it'll be 253 by the time it reaches your router, and your router will ignore it because it says, "Whew, it's 253, it's not 254. So that's a useful one. I mean, it's a bit of a hack, but it's a useful one. It's a useful way of stopping people attacking your BGP session. What else? Both neighbors have to agree to use the feature. It's certainly easier and cheaper on the router to perform than using MD5 because people are always worried about people trying to do MD5 attacks on BGP sessions and so forth. Talked about NANOG 2003, February NANOG 2003. Dave Meyer came and presented about that at one of the sessions, so you can read more about it there. What else? Passwords and BGP sessions. Yep, passwords, they were mentioned this morning, as I said. So again, I tend to advise them. Agree what it is between you and your peer. Once the vendor implementations figure out how, try and change them reasonably often as well. So it's pretty good preventative tool, especially when combined with filters and with the TTL hack for BGP. What else? Use communities to scale the iBGP management. Communities are pretty important. Make iBGP configuration a lot easier. Try and come up with a strategy for different classes of customers and so forth. I've covered them before. I put some more slides in here for some reason for more BGP strategy, but we'll just jump over those. try and come up with something. It generally makes it a lot easier to try and handle things in the network in future. Yeah, so let's just jump over these. Not needed, not needed. So, summary of the last bit, try and use some configuration templates. They do make things a lot easier. Use the Project Gumri ones just for guidance. I mean, they're generally pretty good ones, contributed by quite a lot of people. Another thing that people forget when implementing BGP, try and standardize the configuration. Don't come up with a custom configuration for every router in the network. Try and maybe set up 3 classes of router, 3 classes of BGP configuration, and just use those 3 types of configuration, for example. Be aware of standard tricks to avoid compromise the BGP sessions, so something like the TTL hack. Anything to make your life easier. And there's a lot of work has happened out there, especially being contributed to the Qumri website. So have a look at that. Learn from other people's mistakes. And finally, it's all about scaling. If your network won't scale, then it's simply not going to be successful. So what I've tried to cover in the presentation is, so the main bits you need to be aware of, some of the main scalability issues, and so forth. It's a lot to try and do in 180 minutes, but hopefully it'll point you in roughly the right direction, and at least you know where to go and ask for further information. So that is it. Thank you very much. Hope you found it useful. Beer and Gear starts right now. It was delayed by 15 minutes because we were late. So, if you have any questions, you can ask me now, or during the Beer and Gear, or tomorrow, or Wednesday, or whatever. I'll be hanging around. Okay.